Hey guys, tonight we step out into the kind of darkness that feels clean, like the sky just got freshly washed. You can almost hear the cold settling, turning every sound soft and far away. Above you, the stars look sharp enough to scratch glass, and the horizon is a thin, quiet line where the world runs out of streetlights and excuses. Then the first hint appears, so faint you doubt yourself at first. An easy green glow, like someone breathing color into the night very slowly. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And if you're listening from somewhere cozy, post your location and your local time in the comments. I love seeing how many different nights we're sharing at once. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You're standing near one of Earth's quiet margins, and the northern lights tend to favor margins. Not because they're shy, but because bright, busy places make delicate things hard to notice. High latitudes give you space, darkness, and a horizon that isn't competing with 1,000 LEDs trying to sell you something you don't need at 2 a.m. People will tell you the aurora happens because it's cold. That's the brain doing its favorite shortcut, seeing the obvious and calling it the cause. Cold doesn't power the lights. Cold just shows them off. Winter brings long nights. Long nights bring deep darkness. Deep darkness gives contrast, and contrast is the difference between maybe that's a cloud and, oh, the sky is moving. That's the first relaxing fact. The aurora can be there even when you don't see it. It's not waiting for your attention. It's an ongoing interaction high above the weather, and you only catch it when the conditions below cooperate. Your job is simple. You put yourself in a place where the sky can speak quietly, and you stay still long enough to listen. The geography helps. The aurora isn't pinned to the exact top of the globe like a hat. It tends to form a wide ring around the magnetic pole, an auroral oval that drifts and stretches as Earth's magnetic environment changes. If you could look down from far above, it would resemble a loose halo, brighter in some sectors than others. Never perfectly symmetrical, but remarkably faithful to that polar neighborhood. That ring is why going north is good advice, but not perfect advice. Farther north usually increases your chances, but the most active band often sits around that oval. On some nights, being extremely far north can place you inside a quieter region, while the brighter activity hugs the ring a little farther out. It's not common enough to ruin trips, but it's common enough to make locals sound casually wise when they tell you to settle under the oval instead of trying to stand on the planet's very tip. You feel this in the landscape. The world becomes simpler. Dark trees, pale ground, a wide sky. There's less visual clutter, and that matters more than you expect. In the city, your eyes are always doing accounting, signs, headlights, reflections. Out here, your vision relaxes. It stops scanning for noise and starts absorbing shape. The night itself becomes spacious. And then there's the weather, the practical gatekeeper. The aurora lives far above clouds, but clouds are excellent at blocking your entire relationship with the sky. So the calm edges you want are often places with stable winter air. Nights when the stars look crisp and the darkness feels clean. Cold air can be drier, which can mean clearer skies, especially inland. Not a promise, just a tendency, the kind of tendency that makes people build traditions around watching the sky. You notice it in the way your breath behaves. Each exhale becomes a small cloud that appears and dissolves, and the rhythm of that can be strangely soothing. The soundscape shrinks. Snow under your boots crunches like a secret. Far away, a dog might bark once, as if it remembered it had a job and then decided it didn't. When the first glow strengthens, it often starts low and quiet near the northern horizon. It can look like a thin wash of light, almost like distant dawn trying to get in early. The funny part is that you might doubt it even while you're staring at it, because your eyes are not built to be art critics in near darkness. In low light, your eyes rely more on rods, great at detecting movement and brightness, less enthusiastic about color, so the aurora can appear pale at first. A camera, collecting light for a few seconds, will often reveal a richer green and even a hint of violet that your eyes may only catch once the display brightens. If you give your eyes time, you begin to see more. Darkness isn't instantaneous. It's a slow adjustment your body makes. Screens sabotage that adjustment. One quick glance at a bright phone and your pupils clamp down like they're offended. So you keep your screen dim or off, and you allow the sky to become your only light source. After a while, the stars sharpen. The Milky Way becomes more than a rumor, and the aurora, if it's active, starts to show structure. Structure is where the experience turns from pretty to how is this real? Bands develop. Curtains form with faint vertical folds, like the sky is hanging fabric from invisible rails. Sometimes the band ripples, as if a gentle wave is passing through it. The movement is slow enough to relax you, but complex enough to keep your mind curious without making it race. It's like watching waves roll in, endlessly varied, never urgent. Wind is the one thing that can break the spell. Calm cold can feel comfortable with the right layers. Windy cold feels like the atmosphere is personally reviewing your choices. So the best nights often come with a kind of stillness. You find a sheltered spot, you settle, and your body stops fighting the environment and starts cooperating with it. Open horizons help too. Water, tundra, fields of snow, anything that lets you see low on the horizon where faint aurora often begins. Sometimes the glow reflects off a frozen lake or a dark bay, and the reflection makes the whole scene feel larger, as if the sky and earth are quietly mirroring each other. Moonlight plays its own subtle role. A bright full moon can wash the sky in silver and soften faint aurora into something harder to notice, the way daylight erases fireflies. A darker moon phase gives the sky back its depth, and the faintest structures become easier to catch. That said, an active aurora can be bright enough to stand up to moonlight, and that contrast, green light against a moonlit snowfield, can look unreal in a quieter, subtler way. And the longer you stand there, the more your sense of scale resets. The aurora makes you feel small, but in a way that's comforting, like being wrapped in something oversized and soft. Your daily concerns don't disappear. They just stop pretending to be the entire universe. The universe, very politely, takes the stage for a while. That's why beneath a quiet polar sky is a perfect place to begin. The northern lights gather where darkness makes them visible, where high latitudes place you under their favored ring, and where the world is quiet enough for you to notice gentle things happening on a planetary scale. The deeper mechanics are waiting above you like invisible architecture. For the moment, all you need is this: a dark sky, a calm night, and the patience to watch the atmosphere turn silence into light again and again. The green glow you've been watching has a strange way of making you forget one basic detail. It's the middle of the night, and the sun is still involved. That feels unfair at first, like you finally got darkness and silence, and the sun still managed to show up in the credits. But it's true. The Northern Lights are a nighttime story that begins in daylight, far away from you, beyond your weather, beyond the thin blue layer of air you breathe, on the surface of a star that never really stops moving. Picture the sun as more than a bright disk. Up close, it's a churning ocean of electrically charged gas, plasma, so hot that atoms can't keep their electrons politely attached. Everything is restless. The surface boils in patterns called granules, like a simmering pot you can't turn down. Only this pot is big enough to swallow 1,000,000 Earths and still have room for drama. Heat rises, cools, sinks, repeats, and every cycle drags magnetic fields along for the ride. Magnetism on the sun doesn't behave like the tidy bar magnet from a school desk. It tangles, twists, snaps, and reconnects. Those magnetic lines are not imaginary decoration. In plasma, they behave like elastic bands running through a glowing fluid, storing energy and shaping motion. When they get stressed, they don't just sigh and relax. They can rearrange suddenly, releasing energy in flashes and eruptions that throw matter outward. And this is where the sun that breathes particles idea starts to feel less poetic and more literal. The sun is constantly shedding material into space. It's not a rare event, not a special mood. It's a steady exhale, an endless stream called the solar wind. You can think of it as the sun's atmosphere expanding outward, thinning as it goes, filling the solar system with moving, charged particles. Space is not empty. It's full of this quiet flow, as real as wind across a frozen lake, just thinner and faster and far less interested in whether you remember to scarf. Most of the solar wind is made of protons and electrons, with a sprinkle of helium nuclei and trace heavier ions. In other words, mostly hydrogen, because the universe loves hydrogen the way your phone loves collecting fingerprints. These particles don't travel like a neat beam. They spread out, guided by the sun's magnetic field, which is dragged into a spiral shape by the sun's rotation. That spiral means the wind doesn't just race straight outward like a thrown spear. It sweeps across space in a broad, curving pattern. And Earth is simply one of the places that happens to be standing in its path. You're standing under a cold sky, but the journey of the aurora begins in a place that is almost offensively hot. The sun's surface is about 5,500 degrees Celsius, already intense enough to make your imagination back away. Then comes the twist. Above the surface sits the corona, the sun's outer atmosphere. It can reach temperatures of 1,000,000 degrees or more. That's one of the famous puzzles of solar physics. Why the corona is so much hotter than the surface below it. It's the opposite of what you'd expect if heat simply faded with distance. The sun, apparently, enjoys refusing simple explanations. Coronal heat matters because it gives particles enough energy to escape. Gravity holds tight, but not tight enough. When plasma in the corona is energized, some of it streams outward, and that outward flow becomes the solar wind. It's like the sun is wearing a loose, glowing scarf of atmosphere, and strands of it are always drifting away. On most days, this wind is gentle by cosmic standards. Gentle still means hundreds of kilometers per second, which is a hilarious word choice if you imagine it near your face. The solar wind varies. There's a slower wind and a faster wind. The faster streams often come from coronal holes, regions where magnetic field lines open outward more cleanly, giving particles an easier exit. Coronal holes can look dark in certain kinds of solar images because they're cooler and less dense than their surroundings, but cooler is relative here in a way that makes human weather feel adorable. Sometimes the sun does more than breathe. Sometimes it coughs. That cough can be a solar flare, an intense burst of radiation, or a coronal mass ejection, where a huge bubble of plasma and magnetic field is launched into space. A coronal mass ejection isn't subtle. It's an enormous parcel of solar atmosphere shoved outward, carrying a tangled magnetic structure like a traveling storm front. If one of those happens to be aimed toward Earth, the aurora has a higher chance of becoming dramatic, brighter, larger, more animated, because more energy and more particles arrive together, like the sun decided your quiet winter night needed a headline. Invisible snow is a comforting comparison because it suggests quiet accumulation, gentle motion, soft persistence. And it fits. The solar wind isn't a roar you can hear from the ground. It's a continuous pressure, a steady tapping of charged particles. If your body were out in space without protection, those particles would pass through you at tremendous speed. You wouldn't feel it as wind in the usual sense because the density is so low, but the physics would still be there, brushing you with energy and charge, and that's why astronauts care about it in a very practical way. The distance from the sun to Earth is about 150 million kilometers. In human terms, that number breaks the brain and then stands there smugly. In solar wind terms, it's a commute. At roughly 400 kilometers per second, a parcel of solar wind reaches Earth in around 4 days. At 800 kilometers per second, it arrives in about 2 days. The timing matters because it turns the aurora into delayed conversation. The sun did something, and days later you see a response in the sky. Tonight's display, even the faintest glow, is a message that traveled. It had to cross a whole slice of the solar system before it could become visible above your head. That delay gives the experience a dreamy quality. You're watching light born from a process that began days ago. Your sky is showing you the downstream effect of solar behavior, like a cosmic echo that didn't rush to be heard. It's still the same idea that makes stargazing feel humbling. The universe is never only here and now. It's layered with travel time, with cause and effect stretched across distances too large to walk. The solar wind doesn't move through a vacuum of nothingness either. It creates a vast bubble around the sun called the heliosphere, a region where the solar wind dominates over the thin material between stars. The heliosphere is like the sun's influence zone, its magnetic breath pushing outward until it meets the pressure of interstellar space. That meeting point forms a boundary, almost like a shoreline, where the solar wind slows and changes. It's a soothing thought, the entire solar system floating inside a subtle, invisible envelope of solar outflow, as if the sun is gently insisting all the time that it will not be ignored. One more calming detail: the solar wind is not perfectly smooth. It's turbulent. It has gusts and lulls. It carries waves in its magnetic and electric structure. So what reaches Earth is not a constant, boring stream. It's textured. It's varied. The sun sends a flow, and the flow has moods, even when the sun isn't staging a major eruption. That texture is part of why auroras can brighten and fade unpredictably, even over minutes, and why the sky can go from a quiet glow to a sudden pulse of brightness like someone turned a dimmer switch you didn't know existed. The sun also runs on cycles. Roughly every 11 years, solar activity rises and falls. More sunspots appear near solar maximum, and those sunspots are signs of stronger, more complex magnetic fields. More complexity tends to bring more flares and eruptions, and that can lead to more frequent strong auroras. During solar minimum, the sun is calmer, though calm is relative, the way a large dog can be calm while still being capable of knocking over a table with its tail. Even at minimum, the solar wind continues. The breathing never stops. It's easy to think of the sun as stable because it rises every morning and behaves like a reliable lamp. But it isn't a lamp. It's a living engine of magnetism and plasma, constantly reshaping itself. Tonight's aurora is proof that space has weather, and that weather starts at the source. The sun's particles are already in your neighborhood, and your night is preparing to translate their arrival into something your senses can understand. You keep watching that faint band of green, and it becomes harder to believe it's linked to a star you can't even see right now. Yet that's the connection: boiling plasma, invisible wind, delayed consequence, quiet polar darkness. The sky above you is like a screen that reveals what normally stays hidden. It turns the sun's breath into gentle light, slow enough to watch without flinching, precise enough to feel like a secret the universe is willing to share. And somewhere inside that thought, your shoulders loosen, because the aurora isn't a random miracle. It's a predictable wonder, not predictable in timing, but in cause. The sun exhales. Space carries that exhale. Your night receives it. The next part is how Earth takes that invisible arrival and shapes it into the moving glow you're watching. That invisible breath from the sun doesn't arrive at Earth like a polite visitor at the door. It comes in fast, charged, and indifferent, a river of particles that would happily slam straight into the atmosphere if nothing stood in the way. And the most calming part of this whole story might be the fact that something does stand in the way, quietly, constantly, without asking for applause. Earth is a magnet, not a dramatic, fridge magnet kind of magnet, more like a planet-sized habit. Deep inside, molten metal moves, and that motion generates a magnetic field that extends outward into space. You don't feel it the way you feel wind or temperature. You notice it indirectly, like a compass needle that insists on pointing a certain way, as if it's being tugged by an invisible string. Most days, that field is just background. Tonight, it's the reason the sky is doing anything interesting at all. When the solar wind reaches Earth, it meets the magnetic field long before it meets air. The field creates a protective cavity called the magnetosphere, a bubble carved out of the solar wind. Picture a boat pushing through dark water. In front of it, the water piles up and diverts. Behind it, a wake stretches out. Earth's magnetosphere behaves similarly. On the day side, facing the sun, it's compressed, squashed inward by the pressure of the solar wind. On the night side, it stretches into a long magnetotail, extending far away from the planet like a trailing ribbon. You're standing on the surface, and this enormous structure is above you, unseen, doing geometry in space. The solar wind hits the front of the magnetosphere and forms a bow shock, an actual shock wave, like the kind created by a supersonic aircraft, except this one is made of plasma and fields rather than air. Most of the incoming particles are deflected around the sides, flowing past Earth as if the planet were a smooth stone in a stream. That deflection is the shielding trick. It's not perfect, but it's impressive. If Earth didn't have this field, the solar wind would interact directly with the upper atmosphere far more aggressively. Over long time scales, that kind of interaction can strip atmospheres away. You don't need to turn this into a horror story. It's enough to appreciate that you're breathing under a roof that also happens to be a magnetic force field. Science fiction loves to pretend that planetary shields are futuristic technology. Earth has been doing it for a very long time, which is both reassuring and mildly irritating if you enjoy feeling special. But the aurora isn't made by the particles that get diverted. It's made by the particles that get guided. Charged particles in a magnetic field do something elegantly strange. They don't usually move straight across the field lines. They spiral around them. Imagine a bead sliding along a wire while also circling it, tracing a helix. That's the motion. Forward along the line, rotating around it, a quiet dance dictated by electromagnetism. So when solar wind particles enter Earth's magnetic environment and become trapped or guided, they start following the architecture of the field like travelers on invisible highways. The field lines themselves curve out from near the southern magnetic region and loop back in near the northern magnetic region. They are like arcs of influence, extending far into space, then returning. Near the equator, the field lines are more horizontal. Near the poles, they plunge more vertically into the atmosphere. This is why the aurora loves high latitudes. It's not because the poles are magical. It's because the field lines, they're shaped like ramps leading down into the upper atmosphere. Still, the magnetosphere doesn't simply open a door and invite solar particles in. It has boundaries, and those boundaries can be tight. The solar wind carries its own magnetic field, known as the interplanetary magnetic field. When that incoming magnetic field is oriented in certain ways, it can link up with Earth's field through a process called magnetic reconnection. The phrase sounds like a therapy exercise, but it's actually physics with teeth. Field lines break and rejoin, releasing energy and changing connectivity. It's one of the key ways solar wind energy enters the magnetosphere. Think of reconnection as the moment the river finds a gap in the levee. The solar wind's energy and particles can couple into Earth's field and get dragged along. They don't all rain straight down, but they can be pulled into the magnetotail, stored, and then released in bursts. Those bursts are one reason the aurora can suddenly intensify. The magnetosphere is not a rigid shield. It's a dynamic system that absorbs energy and then redistributes it. While you watch the sky, far above you the magnetotail can stretch, twist, and load up like a rubber band being pulled. Then, when conditions are right, it snaps. Again, not literally snapping, but rearranging through reconnection in the tail. Energy is released, and particles are flung earthward along magnetic field lines. This is where the planet's steering becomes visible. Chaos gets funneled, not randomly, but along a geometry that produces arcs, curtains, and bands. It's strangely comforting that the aurora has structure because the field has structure. The solar wind is messy. The magnetosphere is an organizer. It takes that mess and says, you can't just go anywhere. You're going here along these lines into these regions. It's the difference between confetti thrown into a hurricane and confetti guided through a gentle paper chute. You still get motion. You still get unpredictability. But you also get form. Those guided particles don't simply drift downward at their own pace. As they move along magnetic field lines, they can encounter electric fields and plasma waves that accelerate them, giving them extra energy. You can imagine it as a subtle downhill slope that occasionally turns into a moving walkway. The particles spiral, they speed up, they get focused into streams. These streams align with the magnetic field and can form what are called field-aligned currents, often associated with the name Birkeland currents. They connect space and atmosphere electrically, like invisible wiring between the magnetosphere and the ionosphere. You don't need to picture literal wires. Picture a gentle electrical conversation with currents flowing along the lines and returning through the upper atmosphere. The ionosphere, the region of the upper atmosphere where sunlight and energetic particles can ionize atoms, plays along. It's conductive. It responds. It becomes part of the circuit. At high latitudes, there are also regions called cusps, where the magnetic field geometry can allow more direct access for particles. These are like soft spots near the day side, where solar wind particles can more readily enter the upper atmosphere. The aurora doesn't always need a dramatic storm. Sometimes it's simply the system doing its normal exchange, a steady trickle of particles guided into the polar atmosphere. And while all this is happening, the magnetic poles aren't exactly where you might expect if you think in terms of maps. The magnetic axis is tilted relative to the rotation axis. The magnetic pole wanders over time. So the auroral regions are tied to magnetic geography, not perfectly to the geographic north you learn in school. That's why the auroral oval is centered on the magnetic pole, not the geographic pole. Tonight, when you face north and watch the glow, you're aligning yourself with a magnetic reality that doesn't care about your compass rose aesthetics. There's another detail that makes the whole thing feel like a softly designed system rather than a random light show. Particles can be mirrored. As charged particles move into stronger magnetic fields closer to Earth, their spiral tightens, and under certain conditions they can bounce back, reflecting along the field line rather than plunging into the atmosphere. They can oscillate between two mirror points, one in the northern hemisphere and one in the southern, trapped in motion like a bead bouncing between two gentle hands. This trapping contributes to radiation belts and other structures in near-Earth space. For the aurora, what matters is that some particles do reach the upper atmosphere. When they do, they collide with atoms and molecules in the thin air high above you. Those collisions transfer energy. The atmosphere responds by releasing that energy as light. You're not diving into the chemistry yet. You're simply holding on to the idea that the light is the atmosphere's way of letting go of energy it just received. The magnetosphere delivered the package. The atmosphere unwraps it. So you're standing there under a faint green band, and the planet is doing something profoundly elegant on your behalf. The solar wind arrives, full of charged particles and embedded magnetic fields. Earth's magnetic field meets it, deflects most of it, couples with some of it, and guides part of that energy toward the polar regions. The process is not a single step. It's a system of boundaries, reconnections, storage, release, and funneling. An orchestra of invisible forces that results in a visible ribbon of light. You can almost feel the scale shift again. Your body is tiny compared to the magnetosphere. The magnetosphere is tiny compared to the heliosphere. The heliosphere is tiny compared to the galaxy. Yet you're here, watching a ripple of this chain appear as color in the night. There's a quiet irony in how protective and revealing the magnetosphere is at the same time. It shields you from most of the incoming particles, and then, in a controlled way, It permits enough interaction to paint the sky. It's like having a very strict bouncer who also happens to be an artist, turning away the dangerous crowd while letting a carefully selected group inside to put on a show. Earth's field is not sentimental, but it is precise, and precision is soothing. It means the aurora isn't a random flicker from nowhere. It's guided, it's steered, it follows rules, even when those rules produce patterns too fluid and alive to predict moment by moment. You watch the band brighten slightly, then thin, then brighten again, and you're watching the magnetosphere breathe in its own way, responding to pressure, redistributing energy, shaping motion along field lines that you can't see but can absolutely trust are there. The sky continues to move with that slow, deliberate grace. Somewhere far above, particles spiral downward along magnetic paths, and the atmosphere prepares to turn their energy into light. The next thing you start to notice, without trying too hard, is that the aurora doesn't just glow. It chooses shades subtle at first, then more distinct when the display grows stronger, as if the upper air has its own palette and its own rules about when each color deserves to appear. The band brightens and thins in a slow pulse, and the first thing that lands in your mind is how unfairly pretty green is at night. It isn't the loud neon green of signs screaming open, more like a calm, diluted emerald, gentle enough that your eyes accept it without stress. Then a sharper edge appears, almost white at first, and you realize the aurora isn't a single color at all. It's layered. It's sorted. The sky is doing chemistry with manners. That palette comes from a simple, soothing rule. The atmosphere glows in the colors it's made of, and it glows differently depending on how high up the collisions happen. The particles riding down magnetic field lines have energy. They can't keep that energy forever, so they hand it off to whatever they hit. Up high, the air is so thin that hit is a generous word. It's more like a rare bump in a vast, quiet room. Down lower, the air thickens and bumps become more common, like moving from an empty hallway into a crowded theater lobby. When an energetic particle, often an electron, collides with an atom or molecule, it can transfer energy and push that atom or molecule into an excited state. Excited is the polite term. It means the electrons in that atom get kicked into higher energy positions. The system doesn't like staying there. It relaxes back down, releasing the extra energy as a photon light. The color of that light is set by the energy difference between the excited state and the lower state. The atmosphere is basically an enormous, cold, slow-motion light instrument, playing specific notes when you tap it with charged particles. The famous green, the one most people dream of seeing, comes mainly from oxygen. Not the oxygen you breathe down here, but oxygen atoms up high, where sunlight and chemistry have pulled molecules apart and created a thin soup of individual atoms. There's a particular oxygen emission that produces a green photon around 557.7 nanometers. You never need to remember that number, but it's fun to know the sky has exact preferences. Green is oxygen being nudged and then quietly resetting itself, like a calm person putting a book back on the shelf after someone knocked it sideways. Green tends to appear around roughly 100 to 150 kilometers up, sometimes higher, sometimes lower, depending on how energetic the incoming particles are. That height is far above the weather, far above the birds, far above the last place your daily worries can reach without special equipment. At those altitudes, the air is thin enough that the excited oxygen has time to release its green light before it gets bumped again. That time detail matters more than most people expect. Some light emissions happen quickly. Others are slower, almost stubbornly slow, and they need space and quiet to happen at all. Oxygen's red aurora is the best example of this personality trait. Oxygen can emit a deep red light around 630.0 nanometers, and it's gorgeous in a way that feels almost sacred, like the sky briefly remembered it could do velvet. But that red emission takes longer, on the order of a second in many cases, which is an eternity in a world of constant collisions. If the air is too dense, the excited oxygen gets bumped before it can release that red photon. The energy is lost as heat or shuffled into other processes instead of becoming visible light. That's why strong red aurora often appears higher, around 200 kilometers and above, where the atmosphere is thinner, collisions are rarer, and oxygen has the quiet it needs to take its time. It's also why red auroras can be less common, and why they can show up more during stronger geomagnetic activity. Bigger energy inputs can create broader regions of excitation, including higher altitude layers, and the magnetosphere can deliver particles in ways that make those lofty oxygen atoms glow. So the colors are not only about what gas, they're about what gas, at what height, with what collision rate. The atmosphere is sorting the light show vertically, like a layered dessert, except it doesn't melt under pressure and it doesn't ruin your jeans. Then come the blues and purples, which often feel more electric and sharp, like the aurora decided to pick up the tempo for a moment. Those colors mostly involve nitrogen. Nitrogen is the dominant gas in the lower atmosphere, and it shows up in auroral light in a few different ways. Molecular nitrogen can emit blue and purple light when excited. Ionized nitrogen, nitrogen that has lost an electron, can contribute reddish or purplish tones too. The exact mix depends on altitude and energy, and the result can be that the lower edges of a bright auroral curtain take on a purplish fringe, sometimes even a pinkish tint. Pink in auroras often isn't a single pure emission. It's frequently a blend, red from nitrogen or oxygen mixing with blue from nitrogen, layered together in your eyes like watercolor. Cameras can sometimes exaggerate this, because long exposures collect faint colors your eyes struggle to separate in real time. Still, when the display is active enough, you can catch those pink edges with the naked eye, and it feels like the sky is doing a gentle flex just to remind you it has more than one trick. There's a reason the lower edge can look more saturated or more sharply defined. Incoming electrons tend to lose energy as they penetrate deeper. Higher energy electrons can reach lower altitudes before they slow down and start exciting molecules. Lower energy electrons get stopped higher up. That creates an energy-dependent layering. The hardest-hitting electrons can reach into denser nitrogen-rich regions and trigger those brighter blues and purples, while the softer interactions happen higher, where oxygen dominates the visible show in green. All of this turns the aurora into a kind of natural spectrograph. You're watching energy deposit itself at different heights, and the colors are telling you where. Green suggests a certain altitude band. Deep red suggests higher altitude oxygen with enough quiet to glow. Blue and purple suggest deeper penetration into nitrogen-rich layers. It's like the sky is handing you a gentle diagnostic report, only it looks like an art installation. And there's an oddly comforting detail hiding in the physics. The aurora is efficient at turning energy into light, but it also turns energy into heat. Most of what happens in those collisions isn't visible. Light is the part your brain gets to enjoy. Heat is the part the upper atmosphere quietly absorbs. The system is constantly balancing. Energy comes in, energy gets redistributed. The aurora is what happens when the balance includes a visible signature, a little bit of radiance offered to the ground as proof that space and atmosphere are interacting. The phrase forbidden transition sometimes comes up in aurora discussions, and it sounds like a fantasy novel, which helps because it makes the science feel less like homework. In atomic physics, forbidden doesn't mean impossible. It means unlikely under typical conditions, meaning the excited state can hang around longer. Oxygen's green and red emissions are often described this way. The long lifetime is why thin air matters. A forbidden transition needs a quiet room. Dense air is not a quiet room. Thin air is. The upper atmosphere provides the perfect stage. Rare collisions, plenty of time, and a steady supply of incoming energy. This also explains why auroras are mainly a high-altitude phenomenon. Down low, the atmosphere is too dense. Excited states get quenched, bumped back to normal without releasing light. The energy becomes heat instead. So the aurora belongs to that middle to upper region where the air is thin enough to glow but present enough to be struck. Too high and there aren't enough targets. Too low and everything gets smothered. The aurora lives in the sweet spot. You can feel that sweet spot in the way the curtains behave. The folds, the vertical rays, the shimmering edges, those are tied to how particles stream along magnetic field lines and how the excitation happens in columns. A single magnetic field line traces down into the atmosphere, and particles spiraling along, it can create a glowing column. Put many of those lines next to each other, and you get a curtain with fine vertical structure. It's the atmosphere lighting up along the invisible comb of Earth's magnetic field. The green band thickens for a moment, and a faint red haze starts to hover above it, almost like a blush. It might be subtle enough that you question it. That doubt is part of the experience, and it's not your imagination being unreliable. It's your eyes being honest about low light. Your cones, the color-sensitive cells, don't work their best in dim conditions. Your rods dominate, and rods are basically the night watchmen, excellent at detecting motion and brightness, not great at nuanced color. A camera with a few seconds to collect light can make the red look more dramatic than it felt in person. That doesn't make the camera wrong. It makes it differently sensitive. There's a gentle sarcasm in that, if you think about it. Your eyes evolved to keep you alive, not to deliver perfect aurora color grading. Meanwhile, your phone camera, the same device that sometimes makes your face look like a wax statue, suddenly becomes a reliable witness for high-altitude oxygen emissions. Life is jokes. Still, the most satisfying moments happen when your eyes catch the color directly without proof from screen. A bright aurora can make green look truly green, not gray-green. It can make purple edges pop. It can throw a red arc so deep and calm it feels like a quiet fire in the sky. When that happens, it's not only pretty, it's informative. It's telling you the incoming particles are energetic enough, the upper atmosphere is calm enough, and the magnetic funnel is aligned in a way that's delivering a clean stream of excitation. Another peaceful fact, the same physics can happen in the southern hemisphere. The southern lights follow the same rules, just centered around the southern magnetic region. Oxygen and nitrogen don't care which hemisphere they're glowing in. The magnetosphere doesn't play favorites. It's all geometry and energy, and the planet quietly offers symmetrical stages at both ends. You keep watching, and the colors shift with emotion. When the aurora intensifies, the green can brighten into a luminous sheet. When it fades, it can retreat into a ghostly haze. The transitions are slow enough to relax you, but they also carry enough complexity to keep curiosity awake while the rest of you unwinds. The aurora becomes a moving reminder that nature can be both precise and gentle at the same time. And there's a deeper kind of magnificence in realizing that every color you see is an atom or molecule doing a tiny reset. An oxygen atom gets excited and releases green. Another oxygen atom, higher up, takes longer and releases red. Nitrogen molecules down lower flicker blue and violet. Millions upon millions of these events happen, coordinated by incoming particles and magnetic fields, and the result looks continuous to you. The sky appears to paint, but it's really the atmosphere blinking at scales too small to separate. The night stays quiet. The cold stays steady. Above you, the aurora keeps selecting its colors based on altitude, density, and energy, like a calm laboratory that never shuts down. The more you understand the palette, the more soothing it becomes. You're not watching randomness. You're watching rules unfold as beauty, the planet translating invisible impacts into visible calm. That calm chemistry in the upper air keeps doing its quiet work. And once your eyes accept the colors as real, something else becomes impossible to ignore. The aurora isn't sitting still. It doesn't behave like a painted backdrop. It behaves like fabric, like a long curtain hung from an invisible rail and teased by a slow, steady current. The folds sharpen, relax, sharpen again. A band that looked smooth a minute ago suddenly sprouts vertical ribs, thin and bright, like someone combed the light with a fine-toothed comb. Then the whole thing ripples, not chaotically, but with a rhythm that feels almost deliberate. The strange part is that nothing up there has hands. There's no wind the way you think of wind at ground level. No gust physically blowing a sheet of light around. The curtain look is an illusion made from structure. Magnetic structure, particle structure, and wave structure, stacked together until your brain interprets it as cloth. Your brain is doing what it always does, translating unfamiliar physics into a familiar metaphor so you don't panic. Start with the simplest reason the aurora looks like curtains. The particles that create it are being guided along magnetic field lines, and those field lines are arranged in bundles. Imagine a whole fan of invisible strings descending from space into the upper atmosphere. Along each string, particles spiral downward and collide with atoms and molecules, making a thin, glowing column. One string produces one column. 1,000 strings side by side produce a curtain. The vertical rays are essentially the glow tracing those individual strings, and the spaces between rays are where fewer particles are hitting at that moment, or where the emission is weaker. That alone would create a stable-looking drape. But the aurora rarely stays stable. It shimmers. It ripples. The rays appear and vanish, and the curtain seems to sway. That movement is your clue that the delivery of particles is not constant. The magnetosphere and the ionosphere are not static pipes. They're more like a living, humming system full of waves, feedback loops, and small instabilities. Tiny regions where energy piles up and then slips sideways. One of the gentlest ways to picture this is to imagine the magnetic field lines as elastic and the plasma around them as a fluid that can carry vibrations. In space physics, there are waves that travel along magnetic field lines, and one famous family of them are called Alfvén waves. The name sounds like a character from a Nordic saga, which is appropriate because these waves show up most dramatically when you're staring into the Nordic night. An Alfvén wave is a ripple in the magnetic field and plasma combined, moving along field lines like a pulse traveling along a stretched rope. When such a wave reaches the ionosphere, it can accelerate electrons downward or modulate existing particle flows, turning the aurora brighter in some places and dimmer in others, like the sky is being played gently like an instrument. That modulation can be fast enough to look like shimmering. You'll see brightness run along a band, not as a single smooth sweep, but as a traveling flicker. Your eyes track it almost automatically, the way you track a ripple across water. Nothing is actually sliding across the atmosphere like a physical sheet. Rather, the region of strongest excitation is moving because the acceleration and precipitation of particles are changing along the magnetic geometry. The folds themselves, those vertical pleats, also respond to the fact that the magnetosphere is feeding particles into the atmosphere in structured ways. Plasma can form narrow channels and arcs where currents concentrate. Currents are not just abstract bookkeeping here. They shape electric fields, and electric fields shape how particles move. When a system sets up a strong enough electric field along a magnetic field line, electrons can be accelerated downward more efficiently. That creates bright rays. When a field relaxes, the ray fades. When it strengthens again, next door, a neighboring ray flares. The curtain looks like it's fluttering, but it's really the underlying particle faucet turning on and off in slender filaments. Sometimes the aurora looks like it has waves running along its lower edge, like a hemline being lifted and dropped in slow motion. That edge is often sharper because lower altitudes can produce brighter emissions when the incoming electrons have the right energy. When the acceleration shifts slightly, the altitude of maximum excitation can shift too, and your eye reads that as the edge moving. A few kilometers in altitude, at those scales, can change the color mix and brightness enough to look like the curtain is breathing. There's also a kind of fluid instability at work, where the solar wind and Earth's magnetic environment rub past each other. Even without diving into the whole solar wind forecasting world, it's useful to know the boundary of the magnetosphere can behave like the surface between two streams. When two fluids slide past each other at different speeds, waves can form at the interface. In everyday life, you see it where wind shears the surface of water into rolling ripples. In space, a similar idea, often described with the term Kelvin Helmholtz instability, can create large-scale undulations at the boundary. Those boundary waves can feed energy into the magnetosphere, which can ultimately influence auroral patterns. It's a long chain, but it matches what you see. The sky behaving like a surface under shear, forming waves where you wouldn't expect waves to exist. The aurora also has its own kinds of internal pattern making. You might notice little curls and swirls, faint eddies within a broader glow. That's often the signature of turbulence in the plasma environment. Structured chaos, not random noise. Plasma likes to form filaments. It likes to form sheets. It likes to break into smaller structures. And when those structures map down along magnetic field lines into the ionosphere, you see them as fine detail. A bright knot here, a darker gap there, a sequence of rays like teeth in a zipper. At times, the aurora will form a smooth arc that stretches across the sky like a luminous bridge. Smooth arcs can hold for minutes, sometimes longer, like the system found a stable configuration and decided to enjoy it. Then, without warning, that smoothness fractures into multiple parallel arcs or into a rapidly moving set of rays, as if the magnetic and electrical environment shifted into a new mode. The change can feel theatrical, but it's still governed by physics. Shifts in currents, shifts in electric fields, shifts in where and how particles are being accelerated. One of the most hypnotic behaviors is pulsating aurora. This is when patches of auroral light brighten and dim in a steady rhythm, sometimes every few seconds, like a slow heartbeat. It's not always in the dramatic curtain form. It can appear as diffuse blobs of light that wink in and out gently, repeatedly. The mechanism is tied to waves and interactions in near-Earth space that scatter electrons into the atmosphere in bursts. The sky becomes a soft strobe, but without the harshness, more like a distant lighthouse seen through fog, steady and patient. Your brain reacts to these pulses in a surprisingly soothing way. A predictable rhythm invites your breathing to match it. It gives your attention something to rest on. It's the same comfort people find in a metronome, in rain tapping a roof, in waves arriving at a shore. The aurora adds a layer of visual complexity, but it keeps the tempo slow enough that it doesn't demand alertness. It holds your curiosity without turning it into anxiety. Then there are the faster ripples, thin bands of brightness that race upward through the curtain, like someone plucked the fabric and sent a wave through it. These can happen quickly enough that you catch them as motion rather than as a change in color. Again, you're watching the effect of a wave in the electromagnetic system. A change in acceleration propagates along the field-aligned structure and translates in a shifting excitation below. Your eyes translate that into a ripple moving through a glowing drape. The fabric illusion becomes even stronger when the aurora forms what look like folds that converge toward a point overhead, a perspective effect caused by the geometry of the field lines and the way the curtain hangs in space. If a curtain of rays is stretched across the sky, rays near the horizon appear closer together, while rays overhead appear more spread out, the way parallel railroad tracks seem to meet in the distance. You're seeing a three-dimensional structure projected onto your dome of vision, and the result is this sensation that the sky has depth, that it's not just above you, but around you. Occasionally, the aurora forms very fine, bead-like structures along an arc, small bright spots arranged like pearls. They can sit for a moment and then smear into streaks or break apart. Those beads, are the visible imprint of small-scale instabilities in how energy is being delivered. The magnetosphere is feeding the ionosphere, and the ionosphere is responding, and the coupling isn't always smooth. The system can organize itself into periodic patterns, like a vibrating string forming standing waves. The aurora becomes the visible trace of that organization. There's also a delicate feedback between the aurora and the ionosphere. When electrons collide and ionize the upper atmosphere, they increase its conductivity. Increased conductivity changes how currents flow. Changed currents alter electric fields. Altered electric fields change how electrons are accelerated. The aurora is not just a passive screen. It's part of the circuit. That's why patterns can evolve in ways that feel alive. You're watching a system that reacts to its own effects, like a microphone near a speaker creating a controlled hum. Except the aurora usually keeps it prettier and far less likely to annoy your neighbors. What makes this especially relaxing is that the motion isn't frantic. Even in active displays, the movement has a kind of grace. The aurora can surge, yes, but it often surges in waves, in arcs sweeping slowly, in curtains lifting and settling. It's dynamic but not aggressive. It has energy without urgency. It's the opposite of the kind of motion that makes your nervous system brace. The aurora's motion invites observation rather than defense. And every time you see a ripple, you're seeing information. A ripple means energy is being modulated. A flutter means particle precipitation is filament. A pulse means a rhythm in wave, particle interactions above. The sky is giving you a gentle readout of invisible processes, and it's doing it in a language you can understand without equations. Brightness, motion, texture. The curtain shifts again, and for a moment the lower edge looks like it's lifting in slow scallops, a row of soft waves traveling along the band. Your eyes follow, and the rest of your thoughts, emails, errands, the strange need humans have to worry about things that aren't happening right now. Quiet down, because your attention is occupied by something that doesn't need your participation. The aurora will do its thing whether you fret or not. It's a very healthy relationship. There's a kind of grandeur in how many layers of reality are stacked into that one moving sheet. The sun's particles arriving, Earth's magnetic field guiding them, waves traveling along invisible lines, electrons being accelerated in pulses, oxygen and nitrogen responding with color, and your own night vision, turning it all into something intimate. The sky isn't merely glowing. It's behaving. It's expressing the motion of an electromagnetic environment that wraps around the entire planet, and it's doing it with the softness of cloth in a slow breeze. The next time the curtain ripples, the color mix changes slightly at the edge, green thickening, a faint violet hinting at depth, and it becomes clear that motion and color are never separate in this phenomenon. The ripples don't just move the light. They reshape where in the atmosphere the light is being made, and that means the palette shifts with the waves. You're watching a living gradient, a moving spectrum tied to invisible currents, and it keeps offering new detail just when you think you've seen the trick. That moving gradient keeps changing the way you judge distance. One moment, the curtain feels close enough to touch. The next, it feels like it's hanging at the edge of space. And the truth is it's doing both at once. It's a high-altitude phenomenon mapped onto the dome of your vision, and your brain keeps trying to decide whether it's ceiling, horizon, or something in between. And once your eyes get used to watching motion and color together, you start noticing something even bigger than the folds and ripples. The aurora has a favorite address. Not a street address, obviously. More like a ring-shaped neighborhood that circles the planet near each magnetic pole, a glowing belt that shifts and stretches depending on what the sun has been sending and what Earth's magnetic field has been doing with it. People imagine the northern lights as something that happens at the North Pole because that's how cartoons work. Real auroras are more like a halo worn slightly off-center because the magnetic pole isn't the same as the geographic pole, and because space physics doesn't care about your tidy map. If you could float far above Earth and look down at the night side, The aurora would often outline an oval around the magnetic pole, brighter where the system is funneling particles most effectively. That's where the phrase auroral oval comes from. It's an oval, not a perfect circle, because Earth's magnetic field isn't a perfectly centered, perfectly aligned dipole, and because the whole magnetosphere is being pushed and pulled by a solar wind that doesn't show up with consistent manners. You can feel how this matters just by thinking about the view you get from the ground. When you stand at a high latitude and look north, the first glow often starts low on the horizon, then climbs. That's not the aurora rising like a sun. That's you looking toward the ring. The oval is out there, and when you're positioned beneath or near its edge, the show tends to form where your line of sight intersects the most active region. So the secret geography is this. The best aurora watching often happens not at the top of the world, but under that ring. Under the oval, you're close to the action. Too far south, and you're outside the ring, hoping the oval expands. Too far north, and you might be sitting inside a quieter zone while the brighter arc wraps around you at some distance. That's why a person in northern Norway can be seeing a blazing display while someone farther north is staring at a sky that feels strangely empty. It's not personal, it's geometry. There's a calm satisfaction in that. It means the aurora isn't random luck sprinkled over the northern hemisphere. It's organized the way weather systems are organized, with preferred tracks and boundaries. The oval is like a storm belt, but made of light and magnetism instead of clouds and rain. The oval's position is usually described in terms of magnetic latitude rather than geographic latitude. Magnetic latitude is a way of saying how close you are to the magnetic pole, the pole defined by Earth's magnetic field rather than by Earth's spin. It's a better coordinate system for auroras because auroras follow magnetic field lines down into the atmosphere. Your passport doesn't care about magnetic latitude, but the sky absolutely does. When people say that places like Fairbanks in Alaska, Yellowknife in Canada, Tromsø in Norway, and parts of northern Sweden and Finland are reliable aurora spots, they're not just making small talk. Those places sit beneath or near the typical location of the auroral oval. They're in the zone where, on an ordinary active night, the oval is likely to be overhead or close enough that its arcs climb high in the sky. They're also places with long winter nights, relatively low light pollution in many areas, and climates that often deliver clear skies. Practical bonuses that make the magnetic geography even more generous. You can think of it like fishing. The aurora is the fish. The oval is the river. You can stand in a random field anywhere and hope something jumps, or you can stand where the current actually runs. And yes, it's slightly irritating that the universe rewards planning. It would be more romantic if it only rewarded pure-hearted spontaneity. But the universe has always been more of a read the conditions and show up prepared type. The oval isn't fixed. It shifts in response to changes in Earth's magnetic environment. On quieter nights, it can be tighter and closer to the pole. On more active nights, it can expand toward lower latitudes, bringing auroras to places that normally only get a faint glow near the horizon. You've probably seen photos of auroras above cities, much farther south than usual. Those are the nights when the oval swelled, like the system took a deep breath and decided to paint a larger canvas. Even when it doesn't expand dramatically, the oval can wobble. It can brighten in one sector and fade in another. It can stretch and become more asymmetric because the solar wind pressure and the orientation of the incoming magnetic field change how energy couples into the magnetosphere. From above, that oval can look like it's shifting position around the pole, sometimes elongated toward midnight, sometimes toward dawn, sometimes brighter on the dusk side. From the ground, that translates into a simple human experience. One town has a show, another town 30 minutes away has a tease. People text each other like they're chasing a rumor. The local time matters too, in a way that feels weirdly intimate. Auroras are often more likely or more active in certain local time sectors, especially around magnetic midnight, when the magnetotail processes tend to send energy back toward the planet in ways that can intensify particle precipitation. You don't need to turn this into a scheduling obsession. It's enough to notice that late evening through the early morning can be a prime window, not because the aurora is shy earlier, but because the magnetosphere has its own daily rhythm as Earth rotates under the solar wind's influence. And that rotation adds another layer to the geography. You're not simply sitting under the oval. Earth is turning, carrying you through different magnetic longitudes. The oval remains tied to the magnetic pole and the overall magnetic configuration, while you're riding a spinning sphere beneath it. The result is that the same place can have different viewing experiences at different hours, even on the same night, simply because the system's preferred regions sweep over you or slide away. When you hear experienced aurora watchers say the sky turned on, it often means the oval brightened over their sector. It's not that the aurora was absent everywhere and then present everywhere. It's that the active region of the oval rotated into their sky, like the beam of a lighthouse sweeping past. One moment you have a faint haze. 15 minutes later you have vertical rays and a bright arc overhead. Nothing mystical happened at your location. The system simply arranged itself so that your slice of the oval became lively. This is also why the aurora can feel like it has direction. Sometimes the activity is concentrated to the north, hugging the horizon. Other times it climbs overhead and even spills into the southern sky. That spill can be startling the first time you see it, because your brain expects northern lights to stay politely on the north side like a well-labeled exhibit. When it pushes southward overhead, it feels like you're inside the oval rather than looking at it from the outside. You're not watching a distant curtain anymore. You're standing under the stage. The oval's geometry creates a quiet hierarchy of viewing experiences. Near the equatorward edge of the oval, you often see arcs low to the north, sometimes with a stable, elegant shape. Under the center of the oval, you're more likely to see overhead motion, folds, and brighter curtains. More of the dynamic behavior you've been watching. Poleward of the oval, you might see more diffuse glows or occasional structures, but the most intense arcs can be displaced away from your zenith. That's not a rule carved into stone. It's a tendency. The atmosphere and magnetosphere love exceptions, but the tendency is strong enough that it shapes the aurora culture of whole regions. It also explains why people travel to a band of latitude rather than to a single point. In North America, that band curves across Alaska and northern Canada. In Europe, it runs through northern Scandinavia and sometimes Iceland, depending on conditions. In Russia, it stretches across vast northern territories where the sky can be enormous and the light pollution can be almost non-existent if you're far from cities. Each of these regions sits under the oval often enough that you're not gambling on a once-a-decade miracle. You're showing up where the system frequently performs. The southern hemisphere has the same architecture, just with fewer convenient roads and a lot more ocean. The auroral oval around the southern magnetic region often lies over the Southern Ocean and Antarctica, which means the best consistent viewing is less about charming towns and more about remote coastlines and rugged latitudes. Southern New Zealand, Tasmania, parts of southern Australia, and southern Chile and Argentina can sometimes catch the glow when conditions and skies align. The physics is symmetric, but the human access isn't. The planet is quietly fair. Geography is not. If you zoom out even more, the oval begins to feel like a fingerprint of Earth's magnetic connection to space. It marks where field lines and currents couple most efficiently with the upper atmosphere. It's the visible edge of an invisible boundary between a protected region and an interacting region. Inside the oval, the magnetosphere is still shielding you, still deflecting most of the solar wind, but it's also channeling enough energy along certain paths to make the atmosphere glow. The oval is where the conversation between space and air becomes loud enough for your senses. That's the secret that makes auroras feel both mystical and logical at the same time. From the ground, you see something that looks like living light. From above, it traces a ring-shaped region dictated by magnetic geometry. Those two perspectives fit together perfectly, and there's a calm in realizing they're not competing explanations. The aurora is beautiful because it's structured. It's mysterious because the structure is invisible until it lights up. You can stand under a bright arc and feel like the sky chose you personally, like you were the only person awake in the world who deserved this. Meanwhile, the oval is simply doing what it does, wrapping around the magnetic pole and shifting its brightness along different sectors. It doesn't care about your schedule, but it does care about field lines and currents, and somehow that ends up feeling more comforting than if it cared about you. Because if it's physics, it will happen again. If it's physics, you can learn it. And if you learn it, you can find yourself under the right part of the ring more often than not. The curtain overhead ripples again, and the motion seems to travel along an arc that curves across the sky, hinting at the larger shape you can't see from the ground. You're inside a slice of the oval's footprint, watching the system's preferred geography manifest as light. It's like standing under a huge, silent bridge and seeing only the part directly above you. You can't see the whole structure at once, but you can feel its scale from the curve of the arc and the way the rays align. And once you sense that curve, the aurora stops being just up there. It becomes a place, a ring, a belt, a boundary, something with location and shape. The night becomes not just dark, but mapped. You're standing on a rotating planet under a shifting oval of light, and the grandeur isn't only in the colors or the motion. It's in the geography itself, a planetary halo that appears where invisible lines meet thin air, repeating night after night, as if Earth is quietly wearing its connection to the sun on the outside for anyone patient enough to look up. That sense of the auroral oval as a living geography stays with you as you watch the arc lean and reshape itself. Because once you realize the lights have a preferred, where the next question shows up naturally. What makes a quiet night turn into one of those nights people talk about for years? The kind where the sky stops being a ceiling and becomes a full-on event. The kind where even the skeptical friend who came along for the photos ends up standing there with their mouth slightly open, forgetting to be ironic for once. Those nights usually have shared ingredient, and it isn't luck. It's pressure. Space has weather, and just like Earth weather, it has calm spells and storm systems. The difference is that space weather doesn't rain on your head. It presses on Earth's magnetic shield. When that pressure increases, the whole magnetosphere responds like a living thing being leaned on. It compresses on the day side. It stretches on the night side. Currents strengthen. Boundaries shift. The auroral oval expands and brightens as more energy is pushed into the system, and the atmosphere is asked to glow harder and lower and wider than usual. You've already met the sun's steady breath, that constant solar wind. Storm nights happen when that breath changes character. Faster streams, denser flows, stronger embedded magnetic fields, or those more dramatic parcels like coronal mass ejections. The funny part is that the biggest auroras can begin long before anything looks exciting from your position on Earth. The sky can be perfectly ordinary while the magnetosphere is quietly being loaded with energy, the way a room can feel still right before music starts because someone is setting up speakers behind a closed door. It helps to picture the magnetosphere as a system that can store energy and then release it. When a solar wind arrives with the right magnetic orientation, Earth's field couples more efficiently with it. That orientation detail sounds fussy, but it's one of the most important reasons aurora intensity varies. The solar wind carries a magnetic field. If that field points southward relative to Earth's northward pointing field on the day side, the two can connect more readily through reconnection. Southward orientation is like handing the magnetosphere a key that fits the lock. More coupling means more energy enters. More energy means more magnetic stress. More stress means more dramatic releases. And those releases are often what you see as sudden brightening and motion. So storm nights aren't just more particles. They're more effective coupling. The system isn't only being hit harder. It's being hit in a way that gets under the shield and into the circuitry. A coronal mass ejection is the classic delivery vehicle for that kind of pressure. It's a huge cloud of solar plasma with its own magnetic structure, moving fast enough to cross the Sun-Earth distance in a couple days if it's really hauling. When it arrives, it can drive a shock ahead of it, compressing the magnetosphere and setting the stage for strong activity. Behind the shock, the magnetic field inside the cloud can rotate. Sometimes it turns southward for hours. That's when the coupling becomes efficient, and the aurora can become expansive. Then there are high-speed streams from coronal holes, which can also produce strong auroras, especially when they interact with slower solar wind ahead of them. That interaction region can form a kind of compressed zone, denser, stronger fields, creating what's essentially a space weather front. These stream interaction regions can recur as the sun rotates, because coronal holes can persist and send fast streams repeatedly. That give aurora watchers a slightly eerie experience. The sky can have weekly-ish moods during certain solar configurations, as if the sun is running a schedule it never told you about. On the ground, you don't see the solar wind. You see its consequences. The oval expands. The arcs brighten. Colors intensify. The structure sharpens. A faint band becomes a curtain. A curtain becomes a sweeping canopy overhead. The magnetosphere is being driven harder, and the ionosphere becomes more conductive, allowing stronger currents and more organized precipitation. It's like the whole system turns up its volume. There's a simple human signal of this. The aurora stops looking delicate and starts looking confident. You don't need long exposure to prove it exists. It announces itself. It gains contrast against the stars. It develops distinct edges. The lower boundary can brighten and show purple fringes more clearly as higher energy electrons reach deeper, nitrogen-rich altitudes. The sky begins to feel active, not just luminous. But here's where the day's earlier part matters. Those big nights often begin with solar events that are noticed far from your viewpoint. A flare can happen, and you might only learn about it later. A coronal mass ejection can leave the sun, and it takes time to arrive. During that travel time, forecasters watch how it's moving and estimate its arrival window. When it gets close, satellites upstream of Earth sample the incoming solar wind and magnetic field. That provides a short lead time, sometimes tens of minutes to an hour, before the solar wind hits the magnetosphere fully. That's the moment when the weather report becomes almost immediate, like seeing clouds roll in from the sea. The crucial catch is that the strength of the display depends not only on speed and density, but on the direction of that embedded magnetic field. The field can rotate, and small changes can make big differences. A fast cloud with a northward field can be surprisingly tame. A slightly slower one with a prolonged southward field can produce a memorable night. Space weather has this delicious unfairness where the same headline event can feel very different, depending on a detail you can't see from the ground. It's like ordering a familiar drink and discovering the barista changed one ingredient and your whole evening shifts. Inside the magnetosphere, storm driving creates two overlapping kinds of drama: the broader geomagnetic storm and the more localized substorm activity. The storm is the overall enhancement of currents and energy in near-Earth space, often involving the ring current, a donut-shaped current of charged particles encircling Earth that can strengthen during storms and temporarily reduce the strength of Earth's magnetic field at the surface. You don't feel this reduction directly, but it shows up in measurements, and it's part of what defines a geomagnetic storm. Substorms are more like the magnetosphere's sudden releases of stored energy, especially from the magnetotail. The tail stretches and loads, then reconnects, and energy is dumped into the auroral regions. That's when you see rapid brightening, expansion of auroral arcs toward lower latitudes, and intense motion. If you've ever watched the aurora suddenly explode into activity after a period of quiet arcs, that's the feeling of the system snapping into a release phase. It's not violent in sound. It's violent in electromagnetic rearrangement, which, thankfully, makes the sky beautiful instead of flinging furniture. The easiest way to experience this without overthinking it is to notice how the oval behaves. The pace changes too. A calm aurora can drift and ripple, but storm-driven aurora can surge. Brightness can run along arcs. Rays can flicker more rapidly. Curtains can sweep from horizon to zenith. And yet, even in strong activity, there's often a kind of coherence, a sense that the motion is organized, not random. That coherence comes from the magnetic field still steering everything. The system is louder, but it's still playing its own geometry. Storm nights also make the colors behave differently. During stronger activity, the green can become intense enough to look almost white-green in the brightest regions because your eyes saturate and your rods and cones are both engaged. Purples and reds can appear more clearly because the energy is sufficient to excite the relevant emissions and because the aurora can extend to different altitudes and latitudes. Sometimes you'll see a red band sitting above green, like a two-layer sky. Sometimes a crimson patch will bloom in a diffuse region. Higher altitude oxygen quietly taking its time while the green dances below. The contrast can be so strong it feels staged, like the universe is showing off for an audience. And it's not just the aurora that reacts. The magnetosphere's response to storms can affect radio communications, navigation signals, and power systems under extreme conditions. You don't need to carry those worries into this night, but it's worth holding the scale. The same process painting soft light above your head can also jostle the technological systems humans rely on. That duality makes the aurora feel even more honest. It's not for you. It's a visible symptom of a planetary interaction that has consequences whether you watch it or not. What's soothing is how predictable the ingredients are, even when the outcome feels like magic. Strong solar wind pressure, efficient magnetic coupling, often with a southward component, a magnetosphere that stores and releases energy, an oval that expands, an atmosphere that glows. Each step has its own physics. Together, they create the nights that make people drive for hours and stand in snow without complaining, at least not loudly. There's a particular kind of storm night rhythm you can learn to recognize with your eyes. The display can begin as a stable arc. It holds, it brightens, it starts showing more rays. Then the whole arc can suddenly become more active, thickening and moving as if the system shifted gears. The aurora can expand toward the south, covering more sky. After a burst, it might calm again, returning to arcs and gentle folds, then build toward another burst. That pattern, quiet, build, surge, settle, mirrors the way energy is loaded and released in the magnetosphere. It's a breath pattern at a planetary scale, and once you notice it, it becomes easier to relax into it. Your body likes rhythms, even cosmic ones. If you've ever watched a thunderstorm approach from far away, you know that feeling of the air changing before the storm arrives. Space storms don't change the air you breathe, but they change the feel of the sky if you're tuned in. The aurora can start appearing in places it wasn't earlier, or growing brighter without obvious reason. The oval is shifting. The system is being driven. The night becomes more alive, and you get the quiet privilege of watching the magnetosphere react in real time. And there's something deliciously humbling in realizing that a spectacular aurora is often the late-stage outcome of events that began days ago on the sun. The sun did something. Space carried it. Earth received it. The magnetosphere processed it. The atmosphere answered with light. You're catching the final link in a chain that spans 150 million kilometers, and it arrives with such softness that it never feels like an alarm. It feels like a secret. The arc above you brightens again, and for a moment it looks like the curtain is being lifted from behind the horizon, a gentle reveal. That's the auroral oval reacting to a system under pressure, doing what it does when the solar wind's mood shifts, expanding its footprint, sharpening its structure, and turning the upper atmosphere into a canvas that can handle bigger strokes. The more you watch these changes, the more you start noticing the little oddities that accompany them. Tiny flickers at the edges, brief moments where the aurora seems almost to spark, and even those rare nights when people swear they heard something that matched the light, as if the storm didn't only push on magnetic fields, but also nudge the boundary between what's seen and what's sensed. that thought about hearing something that matches the light tend to sneak up on you at the exact moment you're most willing to believe anything. The sky is already doing impossible-looking things. The cold has sanded the world down to just silence and stars, and your brain is in that soft, receptive state where it stops demanding receipts. So when someone says very calmly, "Did you hear that?" you don't immediately laugh. You pause. You listen harder. And for a second, you can almost convince yourself the aurora just made a sound. People describe it in a few familiar ways. A faint crackle like static, a soft popping like tiny sparks, a whispering swish like someone gently brushing fabric. Sometimes it's described like the sound of dry hair being rubbed between fingers, that small brittle shiver you can feel more than you can hear. The descriptions are oddly consistent across different countries and decades, which is either an argument for something real or an argument for the way human brains borrow the same metaphors when faced with the same kind of uncertainty. Here's the part that makes it genuinely interesting and not just campfire folklore. There are reports from people who aren't trying to be poetic. Pilots, soldiers, researchers, lifelong residents of high latitude, places who have seen auroras since childhood and don't need to embellish them to feel important. Some of them insist they've heard it. Not once, not as a drunken story, but repeatedly under specific conditions. Calm nights, clear skies, strong displays, a certain kind of still air that makes the world feel like it's holding its breath. And then there's the other part, the part that keeps the whole subject balanced. Auroras happen high above you. Really high. Most of the visible light comes from roughly 100 kilometers up and beyond. Sound, as you know it, needs air to travel through, and it doesn't travel well from high-altitude sources to the ground in any direct way. Even if an aurora somehow created sound up there, which already feels like a stretch, that sound would have to travel down through a changing atmosphere, and the timing would be wrong. You'd expect a delay. Light reaches you essentially instantly. Sound would arrive later, and the delay would be noticeable if the sound came from the same source. So when people claim they heard a crackle exactly as a bright wave passed overhead, physics gives you that polite, skeptical cough. Not the rude kind, the kind that says, "Interesting. Explain it." That's the comfortable zone for this topic. The space between something people report and something science hasn't pinned down cleanly. It doesn't ruin the magic. It makes the magic behave like reality. Messy, nuanced, occasionally stubborn. One of the more plausible ideas is that if there is a sound, it may not be coming from 100 kilometers up at all. It may be local. It may be produced near the ground by electrical effects triggered by the same geomagnetic conditions that produce bright aurora. That shifts the whole question from can sound travel from the aurora to me, to can the aurora's electrical environment indirectly cause audible effects right here? Earth's atmosphere is electrically active all the time. There's a fair weather electric field near the surface, and the atmosphere can hold charges in layers, especially under certain meteorological conditions. Calm, clear nights, especially cold ones, can create temperature inversions, where a layer of cold air sits near the ground with warmer air above it. Inversions can trap things, fog, smoke, and sometimes, depending on the setup, electrical charges and ions in near-surface air that can create an environment where small electrical discharges might be more likely to happen close to you, not above you. If a geomagnetic disturbance changes the electrical currents flowing in the upper atmosphere and near-Earth environment, it could, in theory, influence electric fields lower down. And if near-ground objects, dry hair, clothing fibers, grasses, even metal structures, are in an environment where charge differences build and then release, you could get tiny discharges that produce faint crackles. The sound would be local. The timing could appear synced with the aurora because both would be tied to the same underlying electromagnetic disturbance. This idea has a certain quiet elegance. It keeps the aurora high where it belongs, but it allows the aurora's storminess to reach down and tickle the lower atmosphere in ways you might hear. It also aligns with the fact that many reports emphasize very still nights. Still air can make faint sounds easier to notice, but can also help certain atmospheric layers remain stable, giving electrical conditions time to build. Then there's the psychological angle, the one people mention because it's honest, not because it's insulting. Your brain is a pattern-making machine. It doesn't just receive sensations, it predicts them. When you see something dramatic, your brain expects a corresponding sound. If you've ever watched a silent explosion clip on mute and still heard it in your head, you know how ready your mind is to fill in gaps. Combine that with the fact that winter nights can be full of subtle sounds. Ice shifting, trees creaking, snow crystals moving in light wind, distant power lines humming. And it's not difficult to imagine how a person could map a coincidental sound onto a visual cue and feel certain they're linked. But that explanation doesn't fully satisfy the people who insist the sounds are too specific, too repeatable, too clearly tied to moments of intense auroral motion. And honestly, it doesn't need to satisfy everyone. This isn't a courtroom. It's a night under the lights, and the point is to understand the range of possibilities without flattening the experience. There's also the possibility of a kind of electromagnetic to audio conversion happening in the environment. Under strong electromagnetic disturbances, certain objects can act like crude transducers, converting electromagnetic variations into tiny vibrations that could become audible. It's not a comfortable, everyday phenomenon, but it's not a fantasy either. People have heard odd sounds from radio equipment or metal structures during strong electrical conditions. The challenge is that you need conditions that are both strong enough and configured in just the right way to produce a sound you could hear in open air. This is where the honest doubt becomes useful. The most responsible position is neither it's definitely aurora music, nor everyone is imagining things. The responsible position is some people report sounds under specific conditions, and the mechanism isn't conclusively established. That's not disappointing. It's actually rare and refreshing. So many things in modern life get oversold. The aurora doesn't need overselling. It already has the sky. Folklore slips into this space naturally because humans hate leaving a blank. In northern cultures across Scandinavia, Finland, Russia, Canada, Alaska, stories about auroras often treat them as alive. Spirits, ancestors, animals, warnings, celebrations. Some traditions describe the lights as voices or as the sound of the dead moving across the sky. Other stories warn against whistling at the aurora, as if calling to it is an invitation for it to come closer, too close. That kind of warning is an old human pattern. Take something beautiful and powerful and place a boundary around it, because boundaries make us feel safer. It's easy to treat these stories like cute trivia, but they serve a real function. They help people explain a phenomenon that could be bright enough to cast shadows and dynamic enough to feel like the sky itself was alive. If you lived in a world where darkness was deep and winter was long, a sudden luminous storm overhead could feel like a message. Giving it a story gave it shape, and shape gives the mind somewhere to rest. Even today, that story-shaping impulse is still with you. When you hear a faint crackle and see a bright ripple, your mind reaches for a link. It wants the world to be coherent. It wants the aurora to be a single, unified sensory event, seen and heard. That desire isn't weakness. It's how humans experience reality, through connection. At the same time, your calm skepticism can sit right beside your wonder. You could be the kind of person who enjoys the idea of auroral whispers while also knowing the physics is complicated. You can let the possibility exist without forcing it into certainty. That's a surprisingly restful mental posture. Certainty is heavy. It demands defending. Possibility is lighter. It just exists. So you keep listening. You pay attention to the environment, the small noises that belong to the ground. Snow crunching in the distance. A jacket sleeve brushing fabric. The tiny click of ice crystals shifting on a frozen branch. Sometimes a crackle is simply cold wood contracting. Sometimes it's the faint discharge you get when you adjust your hat, and your hair responds with a static complaint. Sometimes it's a distant electrical line, making a sound you never notice in summer, because summer has insects and leaves and 1,000 other distractions. And sometimes, if the night is still enough and the aurora strong enough, you might hear something that feels different, so faint you almost miss it, but so strangely timed that you look up and smile anyway. Even if the sound is local, even if it's your environment reacting to the same broader electromagnetic mood, it's still connected. It's still part of the same system. The aurora becomes not only a visual event, but a cue that the whole air around you is in a different state than usual. That idea can be more satisfying than the fantasy of the aurora making sound directly. It means you're not trying to hear a distant stage. You're noticing your own surroundings responding to space weather. It's intimate. It's like the sky's energy reached down and changed the texture of the night you're standing in. Your attention settles into that texture. The lights continue their slow motion overhead. The cold continues its quiet pressure on your cheeks. Your hearing sharpens, not because you're tense, but because the world is quiet enough for subtle things to matter. Whether the aurora has a sound or simply shares a night with other sounds, you're experiencing something rare, a moment where sight and curiosity and the body's sense of stillness all line up. And even if the mystery remains unsolved, it does something soothing. It reminds you that not everything needs to be pinned down to be real. The aurora can be understood in terms of particles and magnetic fields and oxygen emissions, and it can still leave room for a soft question mark. That question mark doesn't weaken the science. It keeps it honest. It also keeps you listening, because the best mysteries don't demand belief. They invite attention. The curtain above you shifts again, and a brighter wave runs along the arc, like a silent signal traveling through a living system. You listen for a moment, just to see what the night wants to offer. And while you're listening, another gentle truth slips in. The way you perceive these lights, colors, motion, maybe even sound, is shaped by your own senses, and those senses have their own quirks, their own blind spots, their own little lies that become part of the experience. That little question mark you're carrying, the one about whether you heard something or whether the night simply arranged its own soundtrack, sits in the same part of your mind as another quiet truth. You never experience the aurora directly. You experience it through your senses, and your senses are talented, biased, occasionally dramatic, and sometimes a bit lazy when the lighting is bad. The northern lights are an honest phenomenon, but your eyes are not a neutral instrument. They're a living system designed for survival, not for color accuracy in a frozen field at midnight, which is charming in a way, because it means even the act of seeing the aurora is a collaboration. The sky offers light. Your brain interprets it. Your memory edits it. And your phone camera, if you bring it into the situation, starts behaving like an overeager witness who insists it saw everything, even when it also makes questionable choices. In very low light, your vision shifts into a mode called scotopic vision. That's the fancy way of saying your rod cells take the lead. Rods are excellent at detecting faint brightness and movement. They are terrible at telling you whether something is green or gray-green or the exact shade of mildly haunted mint. Cone cells, the ones responsible for color and fine detail, need more light to work well. So under dim aurora, your eyes might register a pale band, almost white with a hint of green, and you'll wonder if it's just thin cloud glowing from distant light pollution. Then you take a photo, and suddenly the screen shows a vivid green curtain with purple edges and a red wash above it, like the sky decided to become an artist the moment you pressed a button. This is the first night vision lie, and it isn't a lie in the sense of being fake. It's a lie in the sense of being a different kind of truth. A camera sensor collects light over time. Your eyes do not. Your eyes integrate light quickly and then move on, constantly updating. When you set a phone to night mode or take a long exposure with a camera, it's essentially holding its eyes open longer than you can. It stacks photons. It counts faint light that arrives slowly. It has patience your biology doesn't. That's why aurora photography often looks brighter and more colorful than what you remember seeing. The camera didn't invent the light. It accumulated it. It took something that was faint per moment and turned it into something strong per image. You were watching the aurora in real time. The camera was averaging and collecting. Both are valid. They're simply different ways of sampling the same phenomenon. Your eyes also change their sensitivity depending on what you've been looking at. Darkness adaptation is not instant. It takes time for the chemistry in your retina to adjust so that rods become more sensitive. Early in the night, after you've been in any kind of indoor lighting or near a car's headlights, your sensitivity is dulled. You can stand under a sky with a faint aurora and miss it completely. Then, 20 minutes later, without the aurora changing much, you suddenly notice it. People interpret this as the aurora turning on, and sometimes it truly does intensify, but sometimes it's your eyes catching up. The most comical sabotage is the phone screen. One glance at a bright display, and your pupils tighten and your rods lose their advantage. It's like you told your eyes, "Great job adapting. I'm going to reset you because I need to check a notification that is absolutely not urgent." If you want to see faint aurora more easily, the best move is to keep your exposure to bright light minimal. The night rewards patience and a little discipline. There's another subtle shift your eyes make at night. Your sensitivity to different colors changes. In dim conditions, your vision becomes more sensitive to blue-green wavelengths, and reds become harder to see. This is why red flowers look darker at dusk, and why a red aurora can be more elusive than you expect unless it's strong. It's also why that iconic green shows up so well. It sits right in the region your night-adapted vision can still notice. The universe, perhaps accidentally, picked a signature color that your rods are more willing to cooperate with. Even the way you look at the aurora matters. If you stare directly at a faint feature, you might miss it. If you look slightly to the side, you might see it better. That's because the center of your retina is rich in cones, while rods are more abundant a little away from center. So looking past the aurora, using a soft, off-center gaze, can make faint structures pop. It's one of those life lessons disguised as biology. Sometimes you see better when you stop trying so hard. Your brain is involved too. It constantly filters and enhances. If the aurora is moving, your brain may perceive it as brighter and more distinct because motion is meaningful to an organism that once needed to detect predators. A still, diffuse glow can be harder to notice than a rippling edge, even if they have similar brightness. The aurora, conveniently, often shimmers, which gives your visual system the kind of stimulus it's built to detect. Then there's memory, which is not a recording device. Memory is a storyteller. It smooths. It sharpens. It emphasizes what felt important and discards what didn't. You might remember the aurora as more saturated because it was emotionally saturated. Or you might remember it as fainter because you expected fireworks and instead got a quiet green wash, and your disappointment edited the brightness downward. Your experience is not only photons. It's expectation plus attention plus mood. The camera, meanwhile, has its own personality flaws. Modern phones are astonishingly good at low-light photography, but they use algorithms that can make creative decisions. Night modes often stack multiple frames, align them, reduce noise, and boost color. Sometimes they boost color too enthusiastically, because the algorithm assumes you want a dramatic photo. This can lead to the aurora looking more neon than it was, or the sky looking brighter and smoother than it felt. If you use a dedicated camera, you get more control, but also more responsibility. A long exposure can smear fast-moving auroral detail into a soft blur, turning crisp rays into a gentle wash. That can be beautiful, but it's not the same as what you saw in motion. Shorter exposures can preserve structure, but they require higher sensitivity or wider apertures, which can introduce noise. Noise is the camera's version of your brain guessing in the dark. It's random speckling that can mimic faint stars or create grain in the sky, and your camera will happily pretend it's texture. White balance adds another layer of interpretation. Cameras need to decide what neutral looks like. Under a night sky, there is no neutral. If your camera assumes a warm indoor light source, it might tint the whole image blue. If it assumes daylight, it might render the aurora differently. You can make the aurora look colder or warmer, depending on that setting, which is a polite way of saying it's easy to accidentally become an aurora color stylist without meaning to. Even your eyes have a kind of white balance. Your brain adjusts for the color of ambient light, trying to maintain a stable perception of what white is. Under moonlight, snow can look bluish. Under city glow, clouds can look orange. Under a faint aurora, the entire sky can take on a subtle green cast that you only notice after a while, like your brain slowly admitting, fine, the night is tinted. That gradual adaptation can make the aurora feel like it strengthens even when it's stable. At first, your brain might categorize the glow as sky. Later, it categorizes it as aurora, and suddenly it seems more present. Naming changes perception. The moment you identify it, it becomes harder to unsee. There's also the issue of contrast. In a perfectly dark location, a faint aurora stands out better because the background sky is truly dark. In a lightly polluted sky, the background is brighter, and the aurora has to be stronger to separate itself. This is why some people go out on a night when the forecast says aurora likely, see nothing, and assume the forecast was wrong. The aurora may have been there, but the sky background swallowed the contrast. Your eyes, again, are honest. They see contrast more than absolute brightness. Stars can play tricks too. A bright arc can resemble a thin cloud band if you're not used to it. A diffuse green glow can look like thin haze. The aurora's movement is often what gives it away. If it changes shape, if it pulses, if rays appear, it announces itself as aurora. If it's stable and faint, it can sit there quietly and let you doubt it for 15 minutes. The aurora doesn't mind doubt. Doubt is part of the viewing experience, and it's one reason the first clear sighting feels so satisfying. The moment your brain stops arguing and just accepts the sky as luminous. The way you position your body matters as well. Cold makes you tense, and tension changes perception. If you're shivering, you'll look for quick confirmation and then retreat, and faint details will be missed. If you're warm enough to stand still, you'll notice slow changes. The aurora rewards stillness, not because it's shy, but because it evolves over time scales that you only appreciate when you stop moving your attention around like it's late for something. And then there's the funny modern phenomenon of watching the aurora through a screen while the aurora is happening above you. People lift phones and see a brighter, greener version of the sky on the display, then aim their eyes at the real sky and feel slightly cheated. It's like comparing live music to a studio track with heavy production. The live experience is subtler, more dimensional, and more honest, but the produced version hits harder immediately. If you're not careful, the camera can steal the moment by making you chase the best shot instead of letting you absorb the night. Still, cameras can also help you learn. The camera sees colors your eyes might miss, especially reds and purples in faint displays. It can confirm that the glow you're seeing is aurora and not cloud. It can reveal structure. In that sense, it's not an enemy. It's a translator. The key is to treat it like a translator and not like the only trustworthy narrator. There's a calm sweetness in holding both truths at once. Your eyes give you motion, depth, the feeling of the aurora alive in real time. The camera gives you accumulated color and detail, a record of what was present but subtle. If you let your senses do their job first, the camera becomes a supplement rather than a replacement. The night vision lies are really just different modes of truth. Your eyes are tuned for survival. The camera is tuned for collection. Your brain is tuned for meaning. Together, they create the experience you'll carry home. A memory of green light shifting like fabric, a suspicion of red above it, a sense of depth that felt unreal, and that odd moment where you listened for a crackle and instead heard your own breathing and realized how quiet you've become. As you keep watching, the aurora's brightness rises and falls, and your perception tracks it like a living thing. You notice how your eyes catch more as they adapt, how the green seems to settle into the sky more confidently, and how the faint purple edge becomes easier to see when you soften your gaze. The sky is still doing plasma physics, but the way you receive it is physiology and attention. And as that attention steadies, another layer of calm shows up almost without effort. The aurora doesn't only light the sky, it changes your inner state. It quiets the mind in a way that feels biological, like your nervous system recognizes awe as a safe place to rest. That shift isn't just poetic. It's tied to how humans respond to vastness, pattern, and gentle motion. How a light show in the upper air can reach down and make your thoughts slow, your breathing steady, and your body feel like it finally stopped trying to solve everything. That quiet settling inside you, the way your thoughts stopped sprinting and started walking, doesn't happen by accident. It happens because your brain is a pattern hunter, and the aurora is a rare kind of pattern. Vast, slow, and non-demanding. Most patterns in modern life come with instructions. A notification wants a response. A deadline wants a plan. A bright sign wants your money. The lights above you want nothing. They move anyway. They glow anyway. They never punish you for not doing anything about it. So your nervous system does the smartest thing it can do in a safe environment. It downshifts. You feel it first in your breathing. Cold air encourages deeper breaths, not because you're forcing it, but because shallow breathing in cold feels unsatisfying, like sipping air through a straw. You take in a fuller breath, and the exhale is visible, which makes the rhythm even more obvious. When the aurora pulses, even gently, your breathing starts to match that pacing the way it matches ocean waves. It's not a mystical alignment. It's your brain using an external rhythm to steady an internal one. Humans do this constantly. You do it with music, with walking, with rocking a child, with rain on a roof. The aurora just happens to be rhythm painted across the sky. Then the mind does something quiet and useful. It stops scanning for threats. In a city, your attention is always partly on guard, even if you feel calm. Cars, strangers, sudden noise, constant motion. Your brain is built to monitor. Under the aurora, especially in a wide, open, quiet place, there's less to monitor. The horizon is stable. The soundscape is sparse. The biggest motion in your world is overhead, and it's slow enough that it never reads as danger. That frees up attention. You can spend it on looking, on noticing, on being present without the constant background question of what you should do next. It has a particular flavor here. It doesn't feel like excitement in the caffeinated sense. It feels like your sense of scale just got rebalanced. You remember the magnetosphere above you, the solar wind arriving days after leaving the sun, the atmosphere responding with exact colors. That chain of cause and effect is enormous, and you're a small part of it. Strangely, that can be comforting. Being small in a hostile universe would be terrifying. Being small in a universe that still makes room for beauty can feel like relief. Your problems shrink, not because they're trivial, but because they finally have competition. There's also something psychologically soothing about watching something that is both complex and predictable. The aurora has rules. It has preferred regions. It has a palette tied to oxygen and nitrogen. It follows magnetic geometry. Even when it surprises you within a framework. Your brain likes that. A world that is only chaos is exhausting. A world that is only routine is boring. The aurora sits in the sweet spot, structured surprise. It gives your mind a puzzle that doesn't demand solving. You can appreciate the mechanism without needing to fix anything. That's part of why the lights can feel oddly intimate. They're planetary scale, but they invite a personal kind of attention. You can watch a bright ray flare and fade, and your brain treats it like a small event you're allowed to witness up close. It's the same feeling you get watching a candle flame, except the flame is 100 kilometers up and the candle is the entire upper atmosphere. You're looking at energy arriving, being transformed and released as light. The conversion is gentle, continuous, and hypnotic. Cold plays its own role in this mental shift, and it's worth appreciating without romanticizing frostbite. Cold makes the world sharper. Sounds carry differently. Smells are cleaner. The air feels thin and crisp against your nostrils. Your skin notices boundaries. In a warm room, your senses can blur into comfort. In cold, your senses become precise, and precision pulls you out of abstract worry and into the immediate moment. You're not only thinking about the aurora, you're feeling your breath, your gloves, the pressure of boots on snow. It's harder for your mind to spiral into vague anxiety when your body is giving it clear, simple data. And the aurora itself is a kind of soft light that doesn't behave like indoor light. Indoors, light comes from a source. It points. It casts hard shadows. The aurora spreads. It drapes. It doesn't feel like a spotlight. It feels like the sky becoming luminous from within. That kind of lighting does something subtle to your perception. It's diffuse, and diffuse light tends to calm rather than alert. It makes edges softer. It makes the scene feel dreamlike without being unreal. It's as if the world is gently edited, just enough to quiet the urge to categorize everything. You can notice how your thoughts change form while you watch. At first, you might be narrating internally, green brightening, rays, purple edge. Then, after a while, the narration fades. You stop labeling. You start absorbing. This is the mind shifting away from language and into sensation. It's the same shift people chase in meditation, except the aurora does some of the work for you by being compelling without being aggressive. It holds your attention lightly, the way a good bedtime story holds attention, not by shock but by steady curiosity. There's a gentle sarcasm hidden here too. You could spend money on 1,000 productivity tools and still struggle to quiet your mind at night. And then you stand in the cold under a moving green curtain and your brain goes silent on its own. The universe has a sense of humor. It's not cruel. It's more like it's saying, you were always built for this. You just forgot. The social dimension matters, even if you're alone. Humans are deeply responsive to shared wonder. When you know other people are looking up, maybe in another town, maybe across an ocean, posting their local time in a comment section, you feel connected without needing conversation. The aurora becomes a shared roof. That kind of connection is oddly calming because it's low effort. You don't need to perform. You don't need to explain yourself. You simply share a sky. And on the nights when the aurora is strong, it can cast faint shadows. That detail is always slightly shocking because it breaks the brain's expectation that nighttime light comes from a moon or from human infrastructure. When the aurora itself becomes bright enough to affect the landscape, it turns the whole environment into a single experience. The snow takes on a hint of green. The trees become silhouettes against a luminous background. Your sense of night changes. Night stops being absence. It becomes presence. Presence is the key word for sleep, even when it sounds backward. People often chase sleep by chasing escape. Escape can backfire because the mind doesn't like being cornered. Presence is gentler. Presence says, you're here, you're safe, the world is quiet, something beautiful is happening, and you don't need to do anything about it. That message settles into the body. Muscles loosen. The jaw unclenches. The breath becomes slower, not forced, just allowed. The aurora also plays with time in a helpful way. When you're anxious, time feels sharp and fast, like it's chasing you. When you're absorbed in something vast, time feels wider. Minutes stretch. You're not counting. You're watching. The lights move at a pace that encourages that widening. They're slow enough that you don't feel rushed, but active enough that you don't get bored. The mind slips into a kind of gentle tracking mode, like watching clouds on a summer day. Except these clouds glow and obey magnetic field lines instead of wind. Even your posture changes. At some point, you realize you've been standing with your head tipped back, eyes softened, shoulders dropped. That posture is an unspoken signal to your nervous system. You're not braced. You're not hunched over a screen. You're open. It's harder to sustain frantic thoughts in an open posture. The body and mind are not separate systems. They trade signals constantly, and the aurora encourages a posture that says, nothing is about to attack you, and you can afford to look up. There's also the quiet satisfaction of understanding what you're seeing without draining it of wonder. You know the green is oxygen. You know the ripples are waves and currents shaping particle precipitation. You know the oval is a ring around the magnetic pole. Understanding doesn't make it less beautiful. It makes it more stable. It means you're not witnessing an arbitrary miracle. You're witnessing a reliable interaction between a star and a planet. Reliability is calming. It tells your mind the world has order, even in places that look like magic. This is why people chase auroras again and again. Not only for photos, not only for bragging rights. They chase the state it puts them in, awake but not restless, impressed but not overstimulated, curious but not demanding. The lights give you a way to be engaged and relaxed at the same time, which is an unusual combination in adult life. Most engagement comes with tension. Most relaxation comes with boredom. The aurora offers a third option. You keep watching the curtain drift and ripple, and the longer you watch, the less you feel the need to interpret every change. A brighter wave runs along the arc, and you simply notice it. A purple edge appears and fades, and you accept it without chasing it. The mind becomes a quiet observer, and that role is deeply restful. It's not sleep yet, but it's the slope that leads there, the gentle incline where thinking becomes softer and the world becomes enough. And somewhere in that softness, another curious urge appears. Not frantic, just quietly interested about how creatures other than you experience this magnetically shaped light. Because if your brain is this affected by sky that glows, what happens to animals whose lives are guided by magnetic fields, whose migrations and instincts already follow invisible lines the way auroral particles do? That thought about other creatures sits beside you like a quiet companion, because the aurora isn't only a show for human eyes. You're standing there with your clever explanations and your warm layers and your sense of awe. But the sky is also hanging over a world full of animals that don't need a forecast app to know the planet has invisible lines running through it. Some of them live by those lines. It's easy to forget because humans mostly navigate by roads, screens, and stubborn confidence. But there are animals that treat Earth's magnetic field the way you treat a familiar street grid. They sense it. They use it. They build entire migrations on it. And when a magnetosphere is stirred, when space weather pushes and twists the field, when auroral activity rises, those animals are living inside the same electromagnetic mood that's painting your sky. You can't see that mood directly. You see the aurora, the visible signature. They may feel the underlying shift. Start with birds, because birds are the cleanest example of magnetic navigation that doesn't require you to squint too hard. Migrating birds cross continents and oceans on schedules that would impress the most organized person you know. They don't carry maps. They don't ask for directions. Yet many species orient with a kind of internal compass that responds to the geomagnetic field. It's not their only tool. They also use stars, the sun, polarized light at dusk and dawn, landmarks, smell in some cases, but magnetism is part of the kit. There's a calm strangeness in that. You're looking at a glowing arc created by charged particles spiraling along magnetic field lines. And somewhere below that arc, a bird may be using those same field lines as a directional reference without ever seeing the aurora itself. When geomagnetic activity intensifies, the field can become more disturbed. It doesn't break, but it becomes noisier. The directional information can fluctuate. Some studies and observations suggest that during geomagnetic storms, birds can become disoriented, delay migration, or change their routes. It's not a dramatic Hollywood panic. No flocks crashing into the ground in cinematic slow motion, but more like subtle navigation errors, the same way you might take a wrong turn when your GPS glitches and you pretend you meant to do it. That subtlety matters. Animals don't need perfect information to survive. They need good enough signals plus flexibility. A disturbed magnetic field might make a bird lean more heavily on other cues. Stars if the sky is clear, landmarks if it's over land, or simply waiting for calmer conditions. The aurora, from that perspective, is like a bright neon sign telling you the magnetic environment is lively tonight. The bird doesn't need the sign. It may already feel the liveliness. Owls bring a different mood into the scene. They're not migrating across oceans in most cases, but they do live by nighttime sensing. Your night vision is compromised. Theirs is tuned. Your hearing can pick up a hint of wind. Theirs can triangulate prey under snow. When you stand under an aurora, the night feels quiet to you because you've stepped away from human noise. To an owl, the night is full of information, rustles, squeaks, tiny movements, and the soft geometry of air currents. Does the aurora affect an owl's hunting? Possibly in indirect ways. A bright display can increase ambient light levels, and that changes the balance of the night. Prey that relies on darkness for cover might behave differently under a brighter sky. Predators may have an easier time seeing motion. On the other hand, a bright aurora is still diffuse light. It doesn't cast sharp beams the way moonlight can. It's more like a gentle brightening that might shift the night's contrast rather than turning it into day. If you picture an owl perched on a dark branch, its head rotating with that smooth, unsettling elegance, it's not looking up to admire the colors. It's scanning the ground. But the sky's brightness still matters because it changes the background against which silhouettes appear. The aurora can lighten the snowfield, soften shadows, and make the landscape's edges slightly more readable. For a creature whose survival depends on reading edges, that's not trivial. And if you want a detail that feels almost too perfect, some animals, including birds, have magnetite, tiny magnetic particles, in tissues associated with sensing. The idea is that these particles can respond to the geomagnetic field, providing directional information. There are also hypotheses about magnetoreception involving chemical processes in the eye that respond to magnetic fields, making the field visible in some subtle way. The exact mechanisms are still studied and debated, depending on species, but the broad truth is sturdy. Magnetism is part of the biological toolkit for more creatures than most humans ever consider. Reindeer pull the story closer to the places where auroras are common. Reindeer live under these skies as a matter of course. They don't book a tour. They don't check cloud cover. They endure winter because winter is home, and their senses are adapted to a world where darkness can last for long stretches. Their vision is particularly fascinating because reindeer eyes adjust to the extreme seasonal light changes of the Arctic. In winter, when sunlight is scarce, they need to make the most of faint light. In summer, when daylight can be constant, their eyes need to cope with glare. Researchers have noted that reindeer can see ultraviolet light, which humans cannot. UV sensitivity makes sense in a snowy environment because snow reflects UV strongly, and this can increase contrast for things like food sources or urine trails that absorb UV and stand out against snow. Now imagine an aurora washing the sky in green. The aurora's light is primarily visible wavelengths, not ultraviolet in the sense reindeer specialize in, but the bigger point holds. Their visual world is not yours. Their night is not your night. While you're marveling at the aurora as a rare event, they may simply register it as another variation in the ambient light environment, another layer of brightness that shifts and moves. It may subtly change contrast. It may change how shadows fall. It might even influence behavior, whether a herd feels more exposed or more secure, depending on terrain and predator presence. And reindeer, like many animals, may also have a relationship with geomagnetism beyond vision. Large-scale movement across tundra, seasonal routes, orientation in featureless landscapes. Magnetic cues could contribute. Again, not as a single decisive factor, but as part of a suite of cues that help animals maintain a sense of direction when landmarks are scarce and weather can erase visual references. Under stormy geomagnetic conditions, that cue might be noisier. The animal may compensate with other senses, or simply rely on herd movement and memory. There's a comforting humility in that. Humans like to believe that our navigation tools make us superior, but the truth is you can get lost in a shopping mall while a migrating bird crosses hemispheres with no battery. The aurora is a reminder that the planet's field is not an abstract diagram. It's a real, physical feature of Earth that lives in the biology of other beings. Migrations aren't only about birds. Some sea animals show evidence of magnetic sensitivity too. Certain fish, turtles, and even whales are sometimes discussed in this context. You don't need to chase every example tonight, but it's worth holding the idea that magnetism is a global cue used in environments where there are no street signs. Open ocean, featureless tundra, night skies without landmarks. The same field lines you've been imagining above your head extend through these habitats, threading the planet with information. The aurora itself may not guide animals directly. Most animals aren't using it as a beacon like a lighthouse. It's too variable, and it's in the sky, not anchored to a stable point. But auroral activity is linked to geomagnetic disturbances, and those disturbances are what can matter for navigation. The aurora becomes the visible tip of an invisible change. When you see a strong display, you're also witnessing a magnetically loud night, and a loud magnetic night can be a different navigational environment. There's another angle that is less about compasses and more about mood. Many animals have circadian rhythms, internal clocks influenced by light. In high latitudes, winter already stretches and compresses those rhythms in strange ways. A bright aurora can add light to the night, even if not as much as the moon. For some animals, small changes in light can affect activity patterns, when to forage, when to rest, when to hide. The aurora could, in theory, nudge those patterns slightly, especially during long polar nights where any additional light source stands out. The more you think about it, the more the aurora stops being a viewing event and becomes part of an ecosystem. It's not just photons in the sky. It's energy entering the upper atmosphere, modifying ionization, altering currents, and potentially changing the electrical environment that living beings inhabit. Most of those changes are subtle at the ground level, but subtle is exactly what many animals are built to detect. Their world is stitched together by subtlety. You can almost feel your own senses sharpening again as you stand there, not because you're anxious, but because you're noticing how alive the environment is. You hear a faint rustle in the dark, and your mind doesn't jump to fear. It jumps to curiosity. Something small moved. Maybe a fox. Maybe a hare. Maybe just wind in dry grass. The aurora overhead makes the scene feel like a stage, but the real action is often near the ground, quiet and continuous. And if an owl passes overhead, silent flight, a soft shadow crossing starlight, you get a brief reminder of how different another creature's relationship with night can be. You're looking up for beauty. It's listening down for survival. Both of you are using the same environment, just reading different layers of it. The magnetosphere above you is being pushed and pulled, and the auroral oval is responding. In the same broad region, birds might adjust routes, reindeer might shift behavior, nocturnal predators might exploit slightly brighter conditions, prey might change how they move. None of it needs to be dramatic. Nature rarely does drama the way humans do. Nature does small shifts repeated over long periods, which is why it works. There's also a human temptation here, to romanticize animals as if they understand the aurora the way you do. They don't need to. Understanding is your hobby, not their requirement. They respond to cues. They adapt. Their bodies contain sensors you can barely imagine. The aurora doesn't need to be meaningful to them in a storytelling sense. It is meaningful in the only way biology cares about. It's part of the conditions they live within. You keep watching the green curtain ripple, and it becomes easier to imagine the planet as a single, connected system rather than separate layers. Sun to magnetosphere, to upper atmosphere, to light, to perception, to behavior. Your awe isn't only aesthetic anymore. It's ecological and electromagnetic at the same time. You're standing under a light show that is also a sign of an ongoing interaction shaping the environment for everything beneath it, feathered and furred and human. And even if you can't know exactly what an owl feels under aurora, you can respect the likelihood that the night is different for it. Not because of the color, but because the entire world's sensory background, light levels, electrical conditions, subtle cues, has shifted. That respect brings a quieter kind of wonder. You're not just a tourist in the sky. You're another animal on a magnetized planet, temporarily aware of the invisible lines that guide both particles and migrations. The aurora softens again, dimming to a broad green haze. That dimming feels gentle in your body too, as if the world is lowering its voice. And once the voice lowers, the next curiosity that naturally follows is how humans learned to read these skies at all. How stories and science both tried, in their own ways, to make the lights human-sized without making them smaller. The aurora softens into that broad green haze again, the kind that makes you doubt your own eyes for a second, and it feels like the perfect moment to remember how long humans have been doing exactly that, staring up, doubting, then deciding it must mean something. Long before anyone talked about magnetospheres or electrons or oxygen emissions, people still noticed the sky behaving oddly, and they did what humans always do when the universe refuses to explain itself. They built stories sturdy enough to hold their fear and their wonder at the same time. You can almost picture a winter night centuries ago. No electric light, no engines, no constant background glow. A sky like that would have felt deeper, closer, more present. A sudden red aurora might look like distant fire. A bright green curtain might look like a spirit walking the horizon. A rapid, active display might feel like the sky is speaking. When your world is mostly dark and quiet, light becomes a message even if it isn't trying to be one. Different cultures held the aurora in different emotional tones. In some places it was playful, in others it was a warning. In parts of the far north, stories treated the lights as the presence of ancestors, or as the souls of the departed moving across the sky. Some traditions warned against pointing, whistling, or mocking the lights, because if the sky is alive, you don't tease it. That caution wasn't only superstition. It was a boundary, a way to keep people respectful of the unknown, and honestly, it worked better than most modern safety briefings. In other traditions, the lights were connected to animals. Foxes running across snow, their tails brushing sparks into the air, or great cosmic creatures stirring in the dark. Those animal stories make a certain kind of sense when you've watched the aurora ripple like living fur, or flick like a tail swish of light. The human mind doesn't invent metaphors out of nowhere. It borrows them from what the body already knows. Then there are the accounts that feel almost painfully human. People seeing red auroras and assuming war, disaster, or divine anger. It's not hard to understand. A blood-red sky would spike anyone's stress level, especially in a time when smoke and fire were the usual explanation for red light at night. If the sky looked like it was burning, the obvious conclusion was that something important was wrong. The fact that the sky can look like a distant catastrophe and still be a perfectly natural interaction between particles and air is one of the aurora's best tricks. Written records of auroras show up across history in places where people kept careful notes. China, Europe, the Middle East, often described in the language available at the time. Red vapors, heavenly banners, armies in the sky, dragons, fiery clouds. You can feel the writers doing their best with limited vocabulary. They were accurate in the only way that mattered. They described motion, color, position, and duration. They didn't know what caused it, but they knew what it looked like, and those observations still echo in modern descriptions because the phenomenon itself hasn't changed its style. As science matured, the aurora didn't stop being strange. It just became the kind of strange that could be measured. One of the first big shifts wasn't about the aurora itself, but about magnetism. The simple compass needle, quietly pointing north, was the hint that Earth had an invisible field. People learned that this field wasn't perfectly steady. Compass readings could vary by location and time. Magnetic storms could shake the needle. That realization planted a seed. Maybe the sky's lights and the compass's nervous twitch were related. It was a bold thought for a world that still liked its heavens separate from its earth. Then, as the age of electricity arrived, the aurora started leaving fingerprints on human technology, which is how you know a mystery is about to get taken seriously. When telegraph systems spread in the 1800s, operators noticed that during strong auroras their equipment behaved strangely. Lines carried unexpected currents. Signals became distorted. Sometimes, in extreme cases, operators could disconnect their power supplies and still send messages because the geomagnetic disturbance induced currents in the lines. That detail is both fascinating and slightly unsettling. The sky can briefly turn your infrastructure into a passive instrument. Those nights made the aurora more than a curiosity. They made it relevant. When a phenomenon can reach down from space and mess with wires on the ground, people stop treating it like a rumor and start treating it like a field of study. Around the same era, the language of the aurora began to sound more familiar to modern ears. The name aurora borealis is often credited to a period when scientists liked naming things in a poetic Latin style. Aurora for the dawn, borealis for the north. The name is soft, almost too gentle for something that can be driven by storms, but it fits the visual mood. A dawn-like glow appearing where no dawn should be. As instruments improved, the aurora stopped being only a shape and became a spectrum. When spectroscopy entered astronomy, it gave scientists a way to split light into its component colors and identify the signatures of elements. This was an astonishing development for its time, because it meant you could learn what something was made of by looking at its light. You could read chemistry at a distance. And the aurora's chemistry turned out to be both clear and teasing. The green line, so famous now, was measured, and for a while it didn't match any known laboratory emission under ordinary conditions. That mismatch created the idea of a mysterious substance, sometimes called aurorium, because humans will absolutely invent an element rather than admit their experiments are incomplete. Eventually, the mystery resolved the way good science often resolves, not by discovering a new magical material, but by understanding that the relevant emissions are forbidden transitions in oxygen that require thin air in special conditions. The element was familiar. The conditions were the key. That resolution is quietly beautiful. It's a reminder that nature doesn't always hide behind brand new ingredients. Sometimes it hides behind new contexts. Oxygen behaves differently at the edge of space. Nitrogen behaves differently. The aurora is ordinary air placed in extraordinary circumstances. The next major leap came when people started suspecting the aurora was connected to particles from space, not just local atmospheric effects. This wasn't an easy idea to accept at first because space used to be a philosophical concept more than a physical environment. But as understanding of electricity and charged particles grew, so did the plausibility that something could travel from the sun and interact with Earth. One of the more compelling early experimental approaches came from the simple, stubborn desire to recreate a thing in miniature. If you can recreate a phenomenon in a lab, you can test ideas. And someone did exactly that. Christian Birkeland, a scientist who, among other things, had the audacity to bring the aurora into a controlled setting using a device that looks like science fiction even now. He built a kind of miniature Earth, a magnetized sphere in a vacuum chamber, and he bombarded it with electrons, watching where the glow formed. The glow appeared in rings around the magnetic poles of his little sphere, an auroral oval in a jar. It was one of those moments where a messy natural wonder suddenly behaved predictably under the right setup. Birkeland's experiments didn't solve everything, but they strengthened a key idea. Magnetism guides the precipitation of charged particles into polar regions, producing auroral light. It's hard not to admire the mindset. Imagine looking at a glowing sky and thinking, I should build a tiny planet and shoot electrons at it. That's either genius or a sign you were never going to be invited to a normal dinner party again. Either way, it moved the story forward. Birkeland also proposed the existence of currents flowing along magnetic field lines between space and the atmosphere, what you might remember as those field-aligned currents. For a long time, this remained theory and inference. Later, with the space age and satellites, measurements supported the presence of these currents, and they even took on his name in common usage. That's one of the rare moments when a human name actually sticks to an invisible process, not because of marketing, but because the idea was solid and the evidence eventually lined up behind it. Once satellites began sampling near-Earth space directly, the aurora's cause stopped being a distant guess and became a measurable environment. Spacecraft could detect the solar wind, measure magnetic fields, and observe particle populations. Instruments could track how energy entered the magnetosphere, how the magnetotail stored and released it, and how particles were accelerated into the auroral zones. The system you've been imagining, the bow shock, the magnetotail, reconnection, waves, became something you could map with data rather than with metaphor. Ground-based networks joined the effort too. All-sky cameras began recording auroral patterns. Magnetometers on the ground measure disturbances in Earth's magnetic field. Radar systems probed ionospheric flows. The aurora became a multi-instrument conversation. You could watch the light overhead while instruments tracked the currents that accompanied it. The night became not just beautiful, but informative in a rigorous way. And yet, even as the science sharpened, the aurora didn't lose its emotional pull. If anything, it gained depth. The more you learn, the more the aurora becomes a visible surface of an invisible architecture. That's why it's so satisfying to watch it with a little knowledge in your pocket. You're not only seeing color, you're seeing oxygen relaxing, nitrogen shimmering, electrons guided by magnetic geometry, waves modulating precipitation, the auroral oval shifting with space weather. You're watching a planetary system express itself. The human story around the aurora is really the story of how we handle mystery. First, we personify it. Then we measure it. Then we build models. And even after we model it, we still stand under it with the same quiet awe that someone centuries ago might have felt, because knowledge doesn't remove the experience. It just adds layers to it. The most restful part is that the layers don't fight each other. The old stories can coexist with the science as long as you don't mistake story for mechanism. You can appreciate why someone might have believed the lights were ancestors dancing while also understanding the physics of charged particles. One is emotional truth, the other is physical truth. Both can be held gently without forcing them into a single category. You're still under the same sky those earlier observers saw, but you're carrying a different toolkit. You know the aurora is a translation of solar energy into atmospheric light. You know it belongs to an oval of interaction around the magnetic pole. You know the green is oxygen, that the red can require quiet upper air, that the purple hints at nitrogen deeper down. You know storms can drive the whole system louder. And you know with a soft kind of satisfaction that the human urge to make meaning was never wrong. It was just early. The aurora brightens slightly again, as if it heard you thinking about it and decided to remind you it doesn't need your interpretation to exist. And that reminder opens a final, gentle thread in this human story. The aurora isn't only something we watched and named. It became something we learned to predict, to track, to treat as weather, because the same solar moods that make the sky glow also touch the systems we built to run our lives. That idea of the aurora as weather slides into place more easily than you'd expect, because you already live by forecasts without thinking about it. You check clouds before a walk, rain before a drive, temperature before choosing a jacket. The aurora becomes part of that same quiet planning instinct, except the forecast isn't about water and air. It's about charged particles in space, magnetic fields twisting like invisible currents, and an atmosphere that responds by glowing, politely, most nights, and extravagantly when the sun decides to be dramatic. The funny part is how modern this feels and how old it actually is. Humans have always tried to read signs in the sky. The difference is that the signs used to be interpreted as messages, and now they're interpreted as signals. Same impulse, upgraded tools. To predict auroras, people watch the upstream conditions in space the way meteorologists watch an approaching storm front. There are satellites positioned where they can sample the solar wind before it reaches Earth, measuring its speed, density, and the direction of its magnetic field. Those measurements are like a heads up, a change is coming. You can imagine the solar wind as a river flowing toward Earth, and these spacecraft as buoys far upstream reporting the current. When the current strengthens or its embedded magnetic field flips into a direction that couples well with Earth's field, the magnetosphere gets leaned on harder and the auroral oval tends to respond. The direction is the detail that keeps everything deliciously unpredictable. Speed and density matter, sure, but the orientation of the magnetic field carried by the solar wind can make or break a night. A strong stream with an unhelpful orientation can arrive and produce a lot of not much. Meanwhile, a slightly less dramatic stream with hours of favorable orientation can turn the aurora into a full sky performance. It's like planning a party and realizing the guests weren't the problem, the mood was. Space weather is a mood system. Forecasters translate these upstream measurements into indices and probabilities. You've probably seen simple scales that describe geomagnetic activity, numbers that rise when storms are stronger. These indices are useful because they compress a complex global electromagnetic situation into something a human can interpret without needing to be a plasma physicist on caffeine. The cost of that simplicity is that the number can't tell you exactly what the sky will look like above your specific location at your specific minute. It can tell you the system is active. It can tell you the oval may expand. It can hint at latitude reach. It cannot promise you a curtain overhead at 11:17 p.m. while you stand in a field and try not to blink. That gap between forecast and experience is part of what keeps aurora chasing addictive. If it were perfectly predictable, it would become a checklist item. You'd schedule it between errands. The aurora resists being scheduled. It cooperates just enough to reward planning, and just little enough to stay mysterious. Even when the global conditions are favorable, local conditions still have opinions. Clouds don't care about the solar wind. Light pollution doesn't care about your excitement. The moon can brighten the sky and reduce contrast, turning faint aurora into a barely there haze. Snow can reflect light pollution and make the horizon glow in ways that confuse your eyes. Aurora forecasts can be excellent, and your viewing can still be mediocre. Not because anyone lied, but because you're trying to witness a delicate upper atmosphere glow through the messy lens of Earth's lower atmosphere and human infrastructure. And yet, the act of forecasting itself is a quiet triumph. It means we've learned enough about the Sun-Earth connection to treat it as a system that can be monitored. The Sun flings out streams of plasma. Earth's magnetic field deflects and channels them. Energy builds and releases. Particles rain down along field lines. Oxygen and nitrogen glow. You can't control any of it, but you can understand it well enough to say, "Tonight has potential." That's an oddly comforting sentence. It's also practical, because those same geomagnetic moods don't only paint the sky. They also tug at the invisible scaffolding of modern life. You've already heard how telegraph lines once behaved strangely during big auroras, carrying currents they didn't ask for. That wasn't a historical fluke. It was a preview. Long conductors on Earth, power lines, pipelines, undersea cables, can pick up induced currents during strong geomagnetic disturbances. The magnetosphere and ionosphere form a kind of enormous electrical environment, and when that environment changes rapidly, it can create electric fields that induce currents in ground-based infrastructure. The phenomenon sounds abstract until you remember it's the same kind of induction that makes a generator work, changing magnetic conditions producing electric effects. Most of the time, it's manageable. Modern power grids are designed with reliability in mind, and operators pay attention to space whether the way pilots pay attention to turbulence. But during extreme storms, the induced currents can become strong enough to cause issues. Transformers can be stressed, protective systems can trip, and the grid can behave in ways that require careful management. The aurora, in those moments, is the beautiful exterior glow of an electromagnetic disturbance that the technical world treats with respect. Satellites are part of this story too, and it's almost poetic. The very machines that help monitor space weather are also vulnerable to it. A geomagnetic storm can heat and expand Earth's upper atmosphere, increasing drag on satellites in low orbit. Increased drag can alter orbit slightly, which matters for tracking and collision avoidance. Storm conditions can also enhance radiation environments, potentially affecting electronics, sensors, and solar panels. Space is not empty. It's a place with weather, and satellites live in it like boats live in the sea. Then there's navigation. Systems that rely on radio signals passing through the ionosphere can be affected by ionospheric disturbances. The ionosphere isn't a static layer. It's a region of charged particles whose density and structure change with solar radiation and geomagnetic activity. When the ionosphere becomes more turbulent or structured, radio waves can refract differently. Signals can scintillate, rapidly fluctuate, like starlight twinkling, but for radio. That can influence certain communications and positioning systems, especially at high latitudes where auroral activity is strongest. It's slightly amusing, in a tired human way, that people who go aurora hunting often rely on the same technologies that aurora conditions can make less stable. You head out into remote darkness with a navigation app, and the planet's upper atmosphere is having a charged particle party that can make signals behave a bit weird. The aurora is gorgeous, and it also has the side hobby of reminding you you're not in charge. Aviation has its own relationship with auroras. Flights at high latitudes sometimes adjust routes during strong space weather events, partly because of communication considerations and partly because of radiation exposure considerations at high altitudes. Again, you don't need to carry worry about this into your night, but the scale matters. The aurora isn't a local lantern. It's a signature of a global electromagnetic event that touches industries and infrastructure. All of this folds back into why prediction became important. Forecasting auroras isn't only about giving people a reason to stand in snow and feel spiritual. It's also about managing risk and maintaining reliability in a technological society that depends on stable electromagnetic conditions more than most people realize. And despite that seriousness, the forecast experience for a normal person still feels charmingly simple. You look at a number, a map of the oval, maybe a color band indicating likelihood, and you decide whether to try your luck. Behind that simplicity is a whole stack of physics, magnetohydrodynamics in the solar wind, reconnection at the magnetopause, energy transport into the magnetotail, wave, particle interactions accelerating electrons, field-aligned currents coupling into the ionosphere. The forecast distills it into a gentle suggestion. Possible. There's a quiet lesson in that. Complex systems can sometimes be made approachable without being dumbed down. You don't need to know every equation to appreciate the dynamics. You can treat the forecast as a conversation with a vast system. The system says, "I'm active." You say, "I'm paying attention." That's enough. The most satisfying nights are often the ones where you can feel the forecast turning into reality. The oval shifts, the sky brightens, the faint arc becomes visible, the structure sharpens. It's like watching a probability collapse into a scene you can stand under. You're not only witnessing an aurora, you're witnessing a prediction become tangible. And even when the forecast fails you, when clouds block the sky or the magnetic field turns uncooperative at the last minute, there's something oddly soothing in the attempt. Because the attempt itself is a choice to step away from the constant indoor world and put your attention on something bigger than your schedule. The forecast is an excuse to show up. Showing up is half the magic. There's also the gentle skill of learning what activity looks like before it becomes obvious. A faint green arc low on the horizon, a subtle brightening that comes and goes. A patch of sky that seems slightly different than it was 10 minutes ago. These are the small signs that teach patience. They train you to notice, not demand. The aurora doesn't respond well to demanding. It responds very well to attention. And attention, in this setting, becomes more than a viewing technique. It becomes a kind of quiet respect for the system that's running above you. You respect that the sun's magnetic field can arrive in different orientations. You respect that the magnetosphere can store and release energy impulses. You respect that the ionosphere can become structured and change how it conducts. You respect that a forecast is not a promise, but a probability guided by real measurements. That respect makes the experience calmer. You're not fighting the night. You're cooperating with it. The lights overhead begin to show that familiar pattern again. An arc thickening, rays forming, motion increasing. And it feels like the system is gently confirming that all the upstream monitoring and indices and maps were pointing toward something real. The aurora doesn't appear because a forecast said it would. The forecast said it might because the aurora was already being prepared by conditions far beyond your sight. You're arriving at the end of a chain that started with solar plasma leaving the sun, crossing space, and pressing on Earth's magnetic shield. And the longer you stay with that chain, the more the aurora begins to feel like a living interface, a shimmering boundary where the sun and Earth keep touching each other without ever physically colliding. It's intimate at a planetary scale. A star breathes. A planet answers. The answer is light. That intimacy opens a deeper kind of curiosity, one that sits just behind the forecasts and the technology. Earth's magnetic field is not fixed forever. It drifts. It changes. Poles wander. The strength varies over long time scales. The aurora, tied so closely to magnetism, becomes not only tonight's weather, but part of Earth's long story, a story about how a planet maintains a shield and what it might mean when that shield changes. That long story about the shield changing doesn't need a dramatic soundtrack. It happens quietly, the way deep things usually happen, beneath oceans and continents, beneath all the weather you actually feel. Earth's magnetic field isn't bolted in place like a permanent fixture. It's generated continuously by motion, by the slow churning of molten iron and nickel in the outer core, a vast hidden engine turning heat into flow and flow into magnetism. It's almost unfair that the aurora looks so immediate and alive when its deeper driver is so slow and subterranean. The lights flicker in seconds, but the field guiding them is born from a process measured in decades, centuries, and longer. A glow in the upper atmosphere is linked to a dynamo thousands of kilometers beneath your feet. The planet keeps secrets, and then it leaks them into the sky in green. The dynamo idea is simple in spirit and complicated in detail. Conductive fluid moving through an existing magnetic field can generate electric currents, and those currents create magnetic fields that reinforce and reshape the original field. It's a feedback loop. Flow makes field, field influences flow, sustained by Earth's internal heat. Heat from the core, from radioactive decay, and from the slow freezing of the inner core drives convection. Rotation adds organization, nudging the flow into columns and patterns that can maintain a coherent global field. It's not a perfect bar magnet. It's a living, shifting magnetic environment with a dominant dipole component and many smaller features layered on top. Those smaller features are why magnetic north is not a fix that you could draw once and forget. The magnetic poles wander because the field's structure changes as the core's flows change. This wandering is called secular variation, which is a wonderfully understated term for something that can rearrange the invisible geometry that animals navigate by and that auroral ovals trace in the sky. From a human perspective, the pole's movement feels like a curiosity. Maps get updated, compasses require corrections. From the aurora's perspective, it means the stage itself slowly shifts location over time. On the timescale of a single night, The pole isn't moving in any meaningful way. The aurora is guided by the field lines you've got, the ones that exist right now, being flexed by the solar wind. But if you stretch your imagination across decades, the oval's favored address can drift. A town that once sat perfectly under the most active zone can find itself a little off-center later. Another region might slowly become more favored, not dramatically year to year, but enough over a human lifetime that experienced observers notice subtle differences. That's one reason historical aurora records can be strangely valuable. When people wrote about auroras appearing at lower latitudes than usual, it can mean a big storm. But over longer spans, shifts in typical auroral latitude can hint at changes in the field's configuration as well. You wouldn't use a single story as evidence. Humans are creative and occasionally mistaken. But over centuries, patterns start to emerge, and science loves patterns with long memory. Even more telling is the way the magnetic field leaves traces in rocks. When volcanic lava cools, iron-bearing minerals can lock in the direction of Earth's magnetic field at that time, like tiny compass needles frozen in place. Sediments can carry similar signatures. Over geologic time, those signatures reveal that the field has not only wandered, it has flipped. Geomagnetic reversals are the headline-grabbing part of this story, mostly because humans love the word flip when it involves something global. A reversal is when the dominant dipole polarity changes, what you'd call north and south in magnetic terms swap. It doesn't happen overnight. It's not a clean switch like someone toggling a light. It's a complex transition that can take thousands of years, with the field weakening, becoming more multipolar, and then strengthening again in the opposite orientation. If you're waiting for a Hollywood moment where compasses spin and the aurora consumes the sky and everyone panics, the planet is going to disappoint you with its slow professionalism. The core doesn't do jump scares. It does long transitions. During a reversal or an excursion, an incomplete or temporary departure from normal polarity, the field can become less dipole-like and more tangled. In that kind of configuration, the auroral oval concept might become less tidy. The regions where particles funnel into the atmosphere could be more complex, potentially allowing auroral activity to show up at different latitudes more often and in more variable patterns. Not because the aurora is seeking novelty, but because the magnetic map guiding charged particles will be less simple. Even without full reversals, Earth's field strength changes. It can weaken or strengthen over centuries. Local anomalies exist too, regions where the field is weaker than surrounding areas. A weaker field in a region doesn't automatically mean auroras will appear there routinely, because auroras are still largely organized around the global structure and solar wind coupling. But field strength and configuration influence how the magnetosphere responds to solar wind pressure and how particles are guided. In broad terms, magnetism is the gatekeeper. Change the gatekeeper, and the gate's behavior changes. This is where your earlier thought about forecasting and technology loops back in a deeper way. A magnetic field isn't just a pretty guide for auroral curtains. It's a shield that shapes how much solar and cosmic particle energy reaches near-Earth space and the upper atmosphere. The field deflects, redirects, and traps particles in ways that protect the lower atmosphere and the surface from a harsher environment. It's not perfect protection. Nothing is, but it's meaningful protection. A long-term weakening of the field could, in principle, change radiation exposure at high altitudes and in space. It could change how often certain space weather effects become operationally significant. The aurora would still happen, but it might happen with a different personality over centuries. The calming part is that Earth has carried this shield for an unimaginably long time. It has weakened and strengthened, wandered and reversed, and life has persisted through all of it. The field is dynamic, and the planet is used to that dynamism. Humans, with our short planning horizons, tend to treat slow geophysical changes as existential dramas. Earth treats them as Tuesday. And still, it's a little thrilling that the aurora is one of the few ways you can feel the shield at all. You can't see magnetic field lines. You can't hear them, despite the occasional aurora sound rumor you were turning over earlier. You can't touch them, but you can watch the atmosphere glow where those lines intersected. The aurora is the field made visible, at least at the edges. There's also a quiet elegance in how the magnetic field gives the aurora symmetry and asymmetry at once. In an ideal dipole world, you'd expect auroras to mirror nicely between north and south. In practice, the field is tilted, offset, and shaped by the solar wind's direction and Earth's rotation. So the ovals are similar, but not identical in their behavior at any given moment. Over a long time, as the field drifts, that symmetry changes subtly. The planet keeps retuning its own instrument. If you sit with that image, the core as a slow musician, the magnetosphere as a resonant chamber, the aurora as the audible note, you start to see the lights as part of an ongoing performance that predates you and will outlast you. That can be the kind of vastness that either makes you uneasy or makes you relax. Tonight, it leans toward relaxing because it tells you the world is bigger than your worry and bigger in a stable way. Your mind might drift briefly to the question everyone asks the first time they hear about reversals. What would it be like to live through one? The honest answer is that you almost certainly wouldn't notice day to day. Compasses would become less reliable as the field weakens and becomes more complex. Navigation systems that rely on magnetism would need adjustments. Animals that use magnetic cues might shift behaviors and rely more on other senses. Aurora patterns might become less predictable over a long time, but the transition would be slow. Life would adapt in increments the way it always does. The more subtle and immediate reality is that even in normal times, magnetic north is already different from true north, and it changes slowly enough that humans regularly update magnetic models for navigation. That's already your lived experience, even if you've never thought about it. The planet is already dynamic. The aurora is a reminder, not an exception. And if you zoom back into the timescale your body can hold, a night, the changes become almost poetic. The large-scale field sets the framework. The solar wind and reconnection drive the energy. The oval shifts and brightens. Curtains form and ripple. The atmosphere glows. Your eyes adapt. Your breathing slows. A core-generated field and a star-driven wind collaborate to make the sky softly alive for a few hours, and then it fades, leaving you with the sense that you witnessed a private signal from a deep system. That feeling can be strengthened by noticing one more thing. The aurora is not only above you, it's also around the planet, tied to a shield that wraps Earth like a magnetic cloak. You're on the surface of a spinning sphere inside a protective field generated by a molten core, watching that field's interaction with the solar wind made visible as light. That's the kind of sentence that sounds grand until you realize it's also just a description of where you are right now. The lights overhead thicken again into a brighter band, and for a moment, the arc's curve feels like a contour line on a map you can't fully see. The geometry hints at the oval. The oval hints at the pole hints at the field hints at the core. Everything is layered, connected, and still strangely calm. And in that layered calm, the next question arrives gently, almost like the aurora itself is nudging your attention forward. If the lights are the atmosphere's response to energy, and if the field is the guide, what does all of this mean for the air itself? The ionosphere that keeps changing, the thin region where Earth becomes electrically alive, where radio waves bend, where satellites skim, where the aurora is born as chemistry and glow. Because the more you look at the aurora, the more the upper atmosphere stops being a distant concept and starts feeling like a place, fragile, dynamic, and quietly essential. The upper atmosphere becomes a place the moment you realize it isn't up there in an abstract way. It's a real region with structure and behavior, an invisible ocean of thin air that turns electrically alive when the sun presses on Earth's shield. You've been watching that life as light, but the light is only the surface expression. Under it, the ionosphere is shifting. densities rising and falling, currents forming, waves traveling, layers changing conductivity like a living fabric that can tighten or relax depending on how much energy is arriving. The ionosphere begins roughly where the air is thin enough and the sun's radiation is energetic enough to strip electrons from atoms and molecules, creating a mix of ions and free electrons. That process is always happening on the day side. Solar ultraviolet and X-rays create ionization, which is why the ionosphere is there in the first place. At night, without direct sunlight, ionization decreases, but it doesn't vanish. There's still lingering charged material, and at high latitudes, auroral precipitation can add ionization even in deep night, keeping parts of the ionosphere lively when the rest of the planet is settling down. It's a strange thing to picture, the air over your head, so thin it barely feels like air at all, holding currents and charges, acting like a conductor and a lens for radio waves. The same region that makes the aurora possible is also the region that helps long-distance radio signals travel by refracting them back toward Earth. It's a layer you benefit from without noticing, like plumbing or gravity. When the aurora intensifies, it's often because electrons are pouring into the upper atmosphere along those magnetic field lines you've been imagining. That precipitation doesn't just create light, it also increases ionization locally. More ionization means higher conductivity. Higher conductivity means currents can flow more easily. Those currents, in turn, produce magnetic disturbances that can be measured on the ground. So the aurora is not only a glow, it's a sign that the upper atmosphere is actively participating in an electrical circuit that connects space to Earth. There's a quiet grandeur in the circuit imagery because it makes Earth feel less like a sealed sphere and more like a participant in a larger system. The magnetosphere is not a static bubble. It's being constantly shaped by the solar wind. The ionosphere is not just an atmospheric layer. It's a responsive boundary that can carry currents, dissipate energy as heat, and glow when excited. Those currents are sometimes described as forming an auroral electrojet, strong flows in the ionosphere at high latitudes that can intensify during geomagnetic activity. The word electrojet sounds dramatic, and it is, but the drama is electromagnetic rather than cinematic. It's energy moving through a conductive layer. It's the upper atmosphere behaving like a giant wire laid around the planet. You can't see the wire, but you can see the aurora that often accompanies it, and you can measure the magnetic signature it leaves. Waves travel through this region too. Some of the auroras pulsing and shimmering can be linked to wave particle interactions higher up, where electromagnetic waves in near-Earth space can modulate how particles are accelerated and precipitated. Those waves can have rhythms, seconds, tens of seconds, creating auroral pulsations you can literally watch. The sky becomes a display screen for processes happening in a region where air and space are no longer separate categories. It's not hard to understand why people who study this for a living can still sound slightly awed when they talk about it. There are fields of science where you can do everything on paper and never meet your subject in person. Auroral physics isn't like that. You can look up and see the result. The equations aren't floating in isolation. They end in a real sky. The ionosphere also changes shape in response to storms. The upper atmosphere can heat and expand. The distribution of charged particles can become uneven, structured into patches and arcs. Irregularities can form that affect how signals propagate. If you've ever heard that GPS accuracy can degrade during strong geomagnetic activity, the ionosphere is one of the reasons. It can become a less stable medium for radio waves, making signals arrive with slight delays or fluctuations. It's a reminder that the air you never think about is doing complicated things far above you, and those complications can reach into your pocket in the form of a navigation app being slightly less confident. But the most calming way to think about the ionosphere tonight is not as a technical obstacle, but as a soft, responsive layer that makes the aurora possible. It is Earth's skin turning luminous where it is touched by space. The touch is energetic, but the response is gentle. Even when storms are strong, The light is not harsh. It's a slow glow, a moving curtain, a quiet choreography. You've been moving through layers all night. The layers of the aurora's colors. The layers of altitude, where different emissions live. The layers of geography in the auroral oval. The layers of time, from solar events days ago to core processes over millennia. The ionosphere sits right in the middle of these layers, literally and conceptually. It's where space becomes atmospheric, where solar energy becomes heat and light and currents. At some point, that layering starts to feel like a kind of reassurance. Your life is often lived on a single layer: tasks, messages, plans. The aurora forces a wider view. It doesn't ask you to fix anything. It simply makes the wider view unavoidable. A star is interacting with your planet. A magnetic shield is guiding energy. A thin layer of air is glowing. You're standing beneath it, small and safe enough to watch. And the magnificence isn't only in the brightness. It's in the idea that Earth has these protective, responsive systems at all. A molten core generating a field. A magnetosphere deflecting the solar wind. An ionosphere carrying currents and glowing. A planet with an atmosphere thick enough to breathe, but thin enough high up to allow forbidden oxygen transitions to shine. The details line up like an improbable set of permissions, each one enabling the next. The universe isn't obliged to be this interesting. It just is. The curtain overhead shifts again, and you notice how your own attention has changed since the beginning of the night. You're no longer trying to capture the aurora with your eyes like it might vanish if you blink. You're watching more softly. The motion feels slower, or maybe you're slower. The light feels less like an event and more like a background truth. This is what Earth does when the sun sends energy and the magnetic field guides it. There's still mystery tucked inside it. Even with all the science, there are questions that stay open because the magnetosphere is a complex system and the ionosphere is a complex system, and their coupling is a dance between two complicated partners. Models improve, measurements get better, but the aurora retains a certain refusal to be fully domesticated, and that refusal is part of its charm. It can be predicted in broad strokes, understood in mechanism, and still feel personal when it blooms overhead. That personal feeling is not because the aurora is thinking about you. It's because your mind is built to respond to beauty and pattern and vastness, and the aurora hits those circuits cleanly. It gives you wonder without demand. It gives you depth without threat. It gives you a reason to stand still. And standing still has been the theme, even when no one named it. Standing still with the cold on your face and the night above you. You notice that the world becomes simpler. The list of things you have to do shrinks. The future loses its teeth. The past stops replaying its arguments. Everything narrows down to the present. Air, light, breath, quiet. The aurora dims slightly, then brightens again in a soft pulse that travels along an arc. The pulse feels like the planet blinking slowly, not in fatigue, but in rhythm. You remember that this rhythm is driven by waves and currents and stored energy releasing in the magnetotail. And you also remember that you don't need to hold all the terms in your mind to enjoy the sensation. Understanding can be present without being loud. The sky continues its slow transformations. A fold deepens. A ray sharpens, then dissolves. A green band becomes a veil. A veil becomes a haze. The edges soften. The movement becomes less dramatic, more like the lingering after a song ends and the room stays quiet for a moment because no one wants to be the first to speak. Your body recognizes that kind of quiet. It's the quiet after something meaningful. It's the quiet where the nervous system takes the hint and releases. The cold, too, seems less sharp now. Or maybe you've simply stopped fighting it. The air is still crisp, still clean, but your attention has shifted away from discomfort and toward steadiness. Breathing feels automatic, slow, and even. Your jaw is loose. Your shoulders are lower. Your eyes blink more slowly. The aurora, in its own way, has done what the best soothing stories do. It has taken your mind far enough away from itself that it no longer needs to grip. You're still on Earth, still inside the field, still under the oval's reach, still beneath an ionosphere that hums with quiet electrical life. But the urgency that usually rides along with consciousness has thinned. You can sense the planet's systems continuing without you. The solar wind continues. The magnetosphere continues. The atmosphere continues. Nothing requires your supervision, and that realization is deeply restful. It means you can let go, not as a dramatic surrender, but as a simple permission. The world is running. You don't have to push it. The aurora fades into a gentler glow, like the last embers of a fire settling into ash. Stars become more prominent again, crisp pinpoints in the dark. The arc that felt like a bridge a while ago becomes a faint suggestion, a delicate wash of green barely distinguishable from the night. If you look slightly away, using that soft side gaze, you can still catch it, proof that the sky hasn't gone dark, only quiet. And in the quiet, the boundaries between things soften. The horizon feels farther. The cold feels less like an edge and more like a blanket of air. The night feels wide enough to hold anything, including whatever you've been carrying. The aurora has shown you a system bigger than your thoughts, and your thoughts have learned, for a little while, to stop insisting on being the center. The glow thins further, and the scene becomes simpler. A dark sky, a few lingering traces of green, the faintest suggestion of motion that could be your imagination or could be the last slow ripple of particles slipping into oxygen and letting go of energy as light. Either way, it's gentle. Either way, it doesn't ask you to decide. Your breathing keeps its slow pace. Your eyelids feel heavier, not forced, just naturally weighted. The body prefers rhythm and safety, and you have both. The last image that stays with you is not a single dramatic curtain. It's a feeling, a planet wearing a soft halo at the edge of night, a magnetic shield holding its shape while letting a little energy in, an atmosphere answering with color, and you watching it long enough that your mind learned how to quiet itself. The sky is still there, even when you stop looking at it, and the aurora keeps doing what it does whether anyone is awake to notice. The green fades to a faint mist, the kind that feels more like memory than light, and the stars settle into their steady positions, sharp and patient. The cold air moves gently in and out of your lungs, clean and calm, each breath a little slower than the one before, each exhale soft and unhurried, as if the night itself is breathing with you. The world feels uncomplicated in this moment, reduced to quiet essentials. Darkness, air, distance, and that last whisper of glow high above, so far away it can't disturb you, only soothe you. The thoughts that usually jostle for attention begin to lose their edges. They don't need to be pushed away. They simply drift like thin clouds sliding across a wide, empty sky. Nothing is urgent. Nothing needs solving. The planet keeps turning without effort, and the invisible field keeps its gentle hold, guiding the last faint traces of energy into the upper air, where it becomes soft light and then softness again. Your body knows what to do with this kind of steadiness. Muscles loosen, the brow smooths, the jaw rests, the eyelids become comfortably heavy, and the darkness becomes friendly, like a familiar room with the lights turned low. The aurora is almost gone now, and that's okay. The quiet it left behind stays. The night holds you without asking anything back, and the last image dissolves into a simple, calming truth. You are safe, you are still, and you can rest.